No, I'm very happy to welcome David Zilber, that is the head of fermentation lab at Noma. And I don't think I need too many presentations. I've seen that quite a few of you are with the book, the Noma book of Guide to Fermentation, so you know exactly who he is. And I just want to thank also Shalom, because he has been the first one who had the idea and the contact also with David, and so we are very happy to have him here, and so thank you, and I leave
just like before David starts, I just want to say thank you to Molini and Professor Campanini for helping me organize this and happening, and for David, of course, for coming. I was lucky enough to take part of MAD Symposium last summer, and MAD is a branch off of the Noma group. They have a symposium for people in the industry, or also that are not industry, to deal with some of the biggest issues in our industry, in the food industry. Last year was Mind the Gap, and there was an after party after the first day, and I saw Dave, and I kind of just went up to him and approached him. I was pretty drunk, actually, and we started talking, and there was a bunch of other people, and they all like went away, and I just was like, you know what, you need to come. Like, I know I study in this university where a lot of people are going to appreciate what you know and what you do, and they're going to be very thirsty for your knowledge. So ask a lot of questions. It's not every day that we're lucky enough to have somebody like this. So thank you again, Dave, for coming and accepting this, and yeah, enjoy, guys.
Okay, I guess that means I start. I'll just speak loudly instead of using the mic so I can walk around the stage. Does everyone have this code now? Because I need this whiteboard back. Write this down. 20, 50, 310. Cool. Got it? You're all here? Yeah. Use the code? Let's go. Done. Cool. So normally when I teach a class like this, it's for maybe like 10 or 15 interns at Noma at a time. René Redzepi, the chef of restaurant Noma, very much believes that Noma needs to be more than just a restaurant. And the fact that we take in about 150 young, mostly young, but also old chefs a year means that, you know, you can't just come to this restaurant and pick herbs and call it a day and say that you've learned something from some of the best chefs in the world. You also need to actually be taught some of the theories and some of the ways that we actually approach food and try and understand what it can do for a diner in a seat, but also for the world at large. So since we opened Noma 2.0, which is this thing over here, at the beginning of last year, I've taken it upon myself to actually invite all the interns one batch at a time into the lab and spend probably 2 or 3 hours with them, walking them through the world of fermentation and kind of dispelling any misconceptions that they might have, and actually getting them to at least grasp as quickly as you can, because this is something that you can spend your entire life working on and never truly know every single nook and cranny of it. But at least to understand the basics, and definitely to kind of demystify any misconceptions that people might have, because there often are a lot when it comes to fermentation. I've never taught a class this big before. I've never taught at university before. I've never been to university, so this is fun. I feel completely qualified to be up here. I'm no Richard Feynman, but I'll try and crack jokes, and I'm pretty easygoing, so if someone has a relevant question, I believe there's no such thing as a stupid question. If it's genuine, also don't ask questions you already know the answers to. But we're gonna just kind of flow, and if someone doesn't understand something, we have 3 hours today. And that's more than enough time to kind of delve into all the parts of, you know, our tome of knowledge in here. Just feel free to raise your hand or shout something out, and then I'll try to address it. But just to dive in, what is fermentation? What is it? Nobody knows. So it's a good thing I'm here. Really?
Transformation.
No. Transformation of what?
The raw material. Oh my God.
A raw material into
Like preserving food through
but this is a fermented product, and this is not preserved. This would rot if you just left it on the counter. This would not. A soy sauce versus some of the ingredients that go into soy sauce. So it's not just about preservation. The transformation of a raw ingredient is very correct, but what are you transforming? You can transform a raw ingredient by putting an egg into a pan, but you're not fermenting, so there's more to it. So what?
Biological process.
Yeah, but a chicken laying an egg is also a biological process, so we can nail it. Transforming sugars, proteins, fats. Okay, we're close, but no cigar. To me, the box answer, and someone's shutting out glucose, that is very much the technical biochemistry answer to fermentation. It's a very specific pathway in organisms. That is the metabolization of glucose into ethanol. That is like the textbook. If you ask a chemist, what is a fermentation pathway? They're going to talk to you about all the enzymes that yeast uses to break down sugars and produce ethanol as a byproduct. But that's too narrow a description for us. So I'm going to expand that description and say fermentation is, yes indeed, the transformation of one ingredient into another by way of a microorganism. So your microorganism is your frying pan. Your microorganism is the tool you use to take a raw ingredient, and it doesn't even have to necessarily be raw, but your base ingredient, and transform it into something else. Now, that something else, for it to actually be fermentation, has to be useful to humankind. Because if you take an apple and just leave it on a counter, Lord knows it'll be moldy in about 2 weeks' time, kind of oozing out the bottom onto your kitchen counter. And that is absolutely a transformation at the hands of microorganisms into something else, a rotten apple. But that rotten apple isn't going to be safe for you to eat. It hasn't been preserved, and it hasn't transformed into anything delicious or useful to people. In fact, it's detrimental. So the act of transforming food from a raw ingredient into a useful ingredient by way of a microorganism is, in fact, the act of fermentation. And that distinction between a rotten apple and a fermented apple that's good to eat, that'll fill your gut with healthy bacteria, that'll fuel you in the morning, that has a bit of lactic acid and zing to it, that actually tastes delicious. That whole world of intent, that you made something delicious on purpose with the help of microbes, precludes that you, as a human being, decided to do it. Eggs don't fry themselves and turn themselves into omelets, nor does food just ferment itself into something safe for people to eat. People have to actively become a part of this process. It's not just about the raw ingredients and the microbes. There's also human intent and deciding what you're going to grow. Just like a farmer sowing his field. Yes, you can go and forage in the wild and find food for you to eat, to bring back to camp, to bring back to your kitchen, to start cooking with. But beyond that, as a farmer, you're deciding what to plant. You're deciding what you want to see grown. You're deciding what in 6 or 8 months' time you actually get to eat. Fermentation is the exact same thing. It is farming at the microbial scale. It is very much intent. Okay. To explain a little bit of the history of fermentation at Nome, now that we understand what it is, we're going to have to talk about accidents. And accidents are some of the most interesting and useful tools in kind of examining history, because they often lead to great discoveries. Back in 2000 and, it must have been 8 or 9, just a few years after Noma opened, something called the Nordic Food Lab was created by, once again, my chef René, in cooperation with some fellows at Copenhagen University. Now, the Nordic Food Lab was going to be a research facility that served not just Noma, but the Nordics at large, in an attempt to, it started out as an attempt to catalog what was edible in the Nordics at a very academic level. There's this old fable of the cooks at Noma working a dish with wild horseradish that René tested the day before. The foragers bring in wild horseradish and he puts it on the dish and he tastes it before service, and it's a complete disaster, and there's no spice and there's no nothing. And then he gets on the phone to the forager and he's like, "What is this? What did you bring me?" And he's like, "It's wild horseradish." He's like, "How come it doesn't taste like it tasted yesterday?" And he's like, "Well, that's because there's 150 varieties of wild horseradish that grow in Denmark." And it was at that moment that René realized that just going out into the wild and picking what you saw and saying that, oh, this is what I need, wasn't enough. We actually had to catalog and understand nature at a really fundamental level, and thus the Nordic Food Lab was born. So a couple chefs from the restaurant, Torsten Vilgaard and Soren West, started in there alongside some professors or students rather from Copenhagen University, and began this journey. And at that point, René realized, thinking back to when Noma first opened, Noma opened in November of 2003, in the dead of winter. And this was a restaurant that was supposed to use wild and foraged goods. And, maybe just due to bad luck or bad planning, all of a sudden they opened with nothing but onions and beets and potatoes on the menu and a bit of meat, and no wild goods to actually put onto the menu because nature wasn't around for that yet. So that first winter was actually a huge struggle for Noma. And people forget that as famous as this restaurant is today, there was a time long before I started that, they would struggle to fill, even a few tables for lunch, where they would do, 4 guests for dinner on a Wednesday. And it's hard to fathom now, but that was the reality. It was a restaurant that was trying to do something different. No one had heard of the chef. No one went to that part of Copenhagen. And it was really a place where, they were struggling to kind of put their name and their vision out there. So that first initial winter, as hard as it was to kind of make ends meet, if you will, in that restaurant, and actually take in a profit, it did give René and the team time to kind of delve into the books of things, and really kind of research what was actually eaten in the Nordics, and really kind of do this academic research. When they started, they were nothing but cooks who just worked in fancy restaurants in France and in the States. This whole understanding of the natural world was a response that would come out over the decades that Noma was open. It wasn't there at the start, and it had to be discovered. So by the time the Nordic Food Lab came around, René thought back to, okay, well, let's try working on salting. We were reading a lot about that when we were trying to figure out how we could actually preserve these things so we wouldn't have to suffer another winter without ingredients. And basically they went down the road of trying to create pickles and preserves. They didn't think of it as fermenting. They thought of it as just, pouring fresh capers, buds from plants like wild garlic or gooseberries at the height of the season into vinegar and just making a fruit pickle, making salted capers, if you will. And the guys in the Nordic Food Lab started working on that. So they had tons of vacuum bags of, odds and ends packed in salt. And that went on for a whole summer season. Maybe 5 to 6 months later, one of the chefs in the test kitchen brings out a bag of gooseberries that had kind of like inflated. He says to René, you gotta try this. And he's like, what is it? It looks rotten. Like, how long has that been sitting there? It doesn't look like it was preserved properly. And he's like, you just have to try it. And he gave him a spoonful of this murky liquid from the bag, and these were salted gooseberries. They were trying to make gooseberry capers. And it completely blew René's mind. It was salty, but also sour, still sweet, and it had this enormous complexity. It wasn't just sour from the sourness of a berry, it had this lactic acid that kind of wrapped around and bit your tongue. And he realized, oh wow, this is going to be the perfect foil for the seafood we have coming in, for limb-cured oysters, for pike perch, to take little slivers of this and dress it over top as that perfect little bite of acidity that's going to cut through the fish's richness. And he realized, well, what happened here? And with a little bit of research, they realized that this batch of gooseberries had been undersalted. Instead of using the 6 or 8% salt they would use to make capers, like you buy caper berries in the grocery store, it only had a couple percent salt. And that allowed microorganisms to thrive, but not all of them. And they'd realized that at the time they'd made something called a sauerkraut berries. And it was at that moment they're like, okay, sauerkraut. Everyone understood sauerkraut as an ingredient. René had made it in France. But he didn't understand that this was like an act that was taken, that they had fermented something by accident, but that it was actually extremely useful. And that opened the floodgates. They realized, okay, well, if we're going to, run into accidents like this, fermentation probably has a lot of power for us as a restaurant. And then, the goal, the aim in the Nordic Food Lab definitely shifted. And all of a sudden, they were focusing on fermenting and everything they could find, all the literature. And at that time, there wasn't much. Sandor Katz had written, I think, maybe one or two books by then. literature on things like koji, buzzwords, things you hear today, garums, black fruits and vegetables. There was nothing of that back then. And the people in the Nordic Food Lab had to do all of this groundwork, reading scientific papers, trying to translate them from Japanese or Chinese to make sense of it, trying to, call up hippies that lived out in the woods in mainland Denmark to find kombucha mothers and things like that. Because this stuff wasn't at all mainstream. It wasn't at all talked about, and even less, it was nothing that was ever done inside a restaurant. Maybe there's Japanese chefs that work at a really high level that might make their rice wine vinegar, but you didn't see restaurants making soy sauce or misos or things like that. So all this knowledge had to be built, and slowly but surely, Noma kind of built up its world of fermentation. One experiment, one success, lots of failures at a time. So Lars Williams, who was with the restaurant as an R&D chef for about 8 years, and an intern at the time named Ariel Johnson, who ended up getting hired by Noma, who was doing her PhD in flavor chemistry, were then tasked in 2013 by René to take this game to the next level and build Noma's fermentation lab. And that was originally a set of shipping containers that just sat outside the restaurant in the parking lot, and they devised ways to make temperature-controlled rooms for each style of ferment that Noma would produce to use in the kitchen. It had one big shipping container upstairs that kind of served as like a very makeshift kitchen and office to kind of run the ship, and that's where a lot of this research really took off. But I'll get into kind of where we are today, and we'll take a look at some photos of the current lab and the new facility. That's just a little bit of the backstory about how Noma got into fermentation. But now we'll actually kind of delve into what we do at the restaurant. So, like I said, that sauerkraut berries, that initial accident that spurred Noma into this whole world, is one facet of fermentation called lacto-fermentation. Lacto-fermentation is a fermentation pathway that's not like an alcohol fermentation pathway. That is carried out by bacteria that are classified, if you will, by their ability to produce lactic acid. Now, there are bacteria that only produce lactic acid when they come into contact with organic molecules that they can metabolize, like sugars, and then there's lactic acid bacteria that can consume a whole range of things, even some proteins, and produce a whole different flight of metabolites, as they're called, of byproducts. But the key idea here is to say that a lactic acid bacteria is a bacteria that produces lactic acid at some point in its life cycle. Now, classifying all these bacteria from all different walks of the great tree of life under this one term is a completely human convenience. You have to think that calling all of these bacteria that have this one characteristic feature lactobacteria, or lactobacillus, if you will, is just a convenient kind of catch-all that we use as a descriptive label. It's also the same as talking about all four-legged animals as being underneath the same umbrella. Obviously, you have alligators and cows and giraffes, and they're nothing alike, but they do have the one feature of all having four legs. When you get into the world of bacteria, of which there are far more species than there are species of everything you can see on Earth, you realize that yes, there are pathways that come up again and again evolutionarily because they're extremely useful to these bacteria, but these can also be from extremely disparately related organisms. There are bacteria that produce citric acid, and there's also fungi that produce citric acid. And the split between those evolutionary histories is hundreds of millions of years. So yes, you can have microbes that produce the same metabolites, the same useful products, but are quite distantly related. So the entire idea that a bacteria or a microbe is consuming a molecule like glucose is all for the sake of fueling its own life cycle. It needs energy to reproduce, to wiggle around, to explore its environment, to divide and multiply. And it does that by taking in glucose, running it through a really complex system of enzymatic pathways, breaking that glucose down in an attempt to extract chemical energy from that molecule to create ATP for itself. ATP is adenosine triphosphate. It is the molecular unit of currency of all life on Earth. Everything that your body does at the cellular level uses ATP. You process about 1 trillion molecules of ATP a day, which is crazy because you're like, well, that's more than I could ever imagine eating or consuming. And that's the whole point of this thing, is that all these life cycles just recycle ATP. Imagine it like a rechargeable battery. When your cell has to move, when your cells have to move a motor protein down your leg to actually carry some important transmitter or a molecule somewhere in your body, they're using ATP to do that. They're using a little battery pack, sticking it where it needs to go, letting it pop off, then taking that used battery pack, breaking down more glucose so they can make more ATP, and the cycle continues. What happens though when you extract chemical energy from glucose is that you get leftovers. And for every molecule of glucose that gets broken down by a bacteria, we'll name him Jim, you end up with 2 molecules. No. Sorry, that was alcohol, ETOH. Of lactic acid. Now, there's a bunch of different ways that bacteria can go around breaking down glucose to fuel their own metabolisms. Not all of them, not all the enzymes that are used in this process will lead to lactic acid as a result. But the fascinating thing is that the bacteria that figured out this trick, that figured out what enzymes it takes to break down glucose, fuel their life cycle, and leave behind this particular molecule, were developing an evolutionary defense mechanism. Bacteria that produce acids as a byproduct to their own existence actually, in fact, acidify their environment. They acidify the environs that they live in an attempt to eke out any competition. Obviously, if there's glucose there, that's fuel not just for that bacteria, but any other species of bacteria that might be in the area. And if there's one thing that life knows, it's that competition is fierce. So even for bacteria in a petri dish that are just trying to kind of make their way around and divide and multiply, they have to make sure that if they're in that space, they can hoard all of this useful energy for themselves. The evolutionary trick of developing lactic acid as a byproduct actually lowers the pH of the environment, so much so that other things can't grow. Acids completely break down the cell walls of other organisms if the pH gets low enough, and they shrivel up and die. Meanwhile, because this organism has grown up producing this thing, it's developed defense mechanisms to its own byproducts, if you will. So it makes the environment safe for it and it alone, leaves behind lactic acid, and completely transforms that environment. So that environment, we're talking about this abstractly as if this was growing in a petri dish. But what happens if this environment is a head of cabbage, or an apple, or a brine that holds asparagus? Then all of a sudden, this lactic acid isn't just making that environment safe for that bacteria. It is doing that, but it's also transforming this thing that we considered food. And it's making it so nothing else can grow in that place. This is where preservation comes into play. This is how bacteria preserve our food for us. Now, there's plenty of bacteria that go through this same cycle. They break down glucose, they fuel their own life cycle, and they produce something else as a byproduct. Botulism does this, but one of the byproducts it produces is a neurotoxin. That's how it keeps an environment safe for itself. A neurotoxin, technically to the botulism bacteria, is a way of preserving that food for it and it alone. But it is a way of preserving food that is not in any way helpful to human beings. This happens to kind of sit in the Venn diagram of organisms that have interests mutually aligned with ours. We can actually enjoy and tolerate lactic acid. We can put it into our food, have it not be so acidic that we feel sick or ill afterwards, even though if you eat enough of it, you will. And it keeps it safe from other bacteria or harmful microbes that might seek to then consume that food for themselves. And this is the whole act and this whole kind of handshake that we have with bacteria in the world of food preservation and fermentation. So, how do you get this bacteria to work for you? Well, to do that, you have to control the environment and set up some initial conditions. This is something we're going to come back to again and again in this talk. But when you're fermenting, you have to find a way to ensure that the bacteria that you actually want to grow in your product, in your asparagus, in your apple, can do that while keeping out other microbes initially at the start. Once this thing gets going, once there's enough of that lactic acid bacteria thriving in your product, thriving in that environment, it'll take care of business. It'll produce so much lactic acid that nothing else is going to get in there and spoil the batch. But initially, it's a free-for-all. Now, I talk about this in the book, and I was it's the way I just thought about it the entire time I was fermenting. And it seems to be like one of the favorite analogies. But as a fermenter, you're acting as a bouncer to a club everybody wants to get into. If there was no bouncer at that door, drunks, crackheads, party kids, everyone would want to get in, and it would be a raucous mess, a fight would break out, it'd be no fun for anyone inside. As a fermenter, you're acting as the bouncer. You're the guy at the door with the velvet robe, towering big muscle man saying, no, not you tonight, you too drunk, go home. Meanwhile, all the good-looking guys and gals can come on in, drink expensive champagne, and make the party actually somewhere fun to be. And that's the basic idea. You need to understand what tools are at your disposal to work that velvet rope. To say, not you, but you. Those are, well, in the business we call them maybe control points or control parameters. And for lactic acid bacteria, that happens to be salt. Good old NaCl, one of the most important minerals on Earth. Salt has the amazing ability to desiccate an environment by way of osmosis. You add a little bit of salt to something, it changes the electrochemical balance of a solution so much that if there are pockets of lower concentration, it will draw salt into those corners to make sure that everything sits in equilibrium. Now, we can get into the physics of this and talk about how minerals dissolve and ionic compounds and all that, but we can kind of basically skip over that. All you need to know is that for a cell, like Jim over here, who can tolerate salt, we'll build an amoeba that doesn't like to. You have a salt, we'll draw the ions, sodium ion and chlorine ion. And they're sitting up here, and this is an area of lower concentration. They're going to want to get in there or make this amoeba shrivel up to get the water out. And that's the process of osmosis. They just want the entire system to sit in equilibrium. And if your membrane as an organism isn't built just right, you won't be able to tolerate salt in your environment. You will shrivel up and die. That's a sad face on us amoeba now. So, this is why this works. Lactic acid bacteria can actually tolerate a fair bit of salt. Their membranes are built as such that they can actually, either take salt in and have their normal life processes still function, or they're strong enough to actually keep the salt at bay and not have all of their insides kind of pour out, losing water, shriveling up and dying. Every organism on Earth has what's called a water activity level that it can tolerate. Human beings can't drink salt water in the ocean for this reason, because once the salt is inside you, you'll just start basically becoming extremely dehydrated, piss out everything that you need to keep inside you, and you're not actually taking in water, you're losing it for this reason. Same thing for microbes. There are microbes that are extremely well suited to and adapted to living in high salt environments. Those are called halophiles. And to a small extent, lactic acid bacteria are halophiles. There are a lot of bacteria that are also harmful to humans that, lucky for us, can't tolerate salt. And so just by adding a little bit of salt, normally in the range of 2% by weight of your product, you can make an environment safe for beneficial microbes like lactic acid bacteria, but completely intolerable for harmful microbes like botulism or molds or things like that. So that's one of your biggest control points. Another is oxygen. Now, oxygen for lactic acid bacteria is a bit trickier. It's not as black and white as salt. It's not like saying, okay, I've dusted this with salt, nothing's going to grow here except for what I want. Oxygen, it's not like lactic acid bacteria completely shrivel up and die in the presence of oxygen. They're just very well suited to working in its absence. But by removing oxygen, you're also removing something essential to a lot of life forms that would, again, seek to grow in that environment. Lots of molds, in fact, almost all molds, are anaerobic creatures like yourselves. They need oxygen to allow cellular respiration to take place. And so when you remove oxygen from an environment by either submerging your product in water, underneath a brine, let's say, or packing it as such that water is kind of oozing out of it and then making an airtight seal, you're making it so that nothing from that whole branch of life can thrive. Now, there are a lot of bacteria that can thrive in oxygen-free environments, but you're kind of using as many control points at your disposal as possible to make sure that that environment is safe for at least the guys who want to get started. So we've got an environment, an oxygen-free environment. We have salt. And those are our two control points that help this microbe to thrive. Once it does so, you just kind of let it do its thing. You set it, and you've set the parameters, and now you let the party kind of run its course. So lactic acid bacteria, as they work on fruits and vegetables, in fact, really do transform them. Now, this is a very simplified kind of chalkboard drawing of this whole process. But it's rare to find life forms or lactic acid bacteria that are actually this simple and just do that one thing, that just consume glucose and just produce lactic acid. Life forms are a lot more complex than that, and a lot of times they'll need other molecules from their environment and have enzymes and pathways that are dedicated to breaking those down that will either modify their environment and produce interesting flavors, or completely different molecules that you wouldn't think of. I guess there's a lot of Italians in the room, but Parmesan cheese, the umami that you taste when you bite into an age of 2-year Parmigiano Reggiano, that actually comes from certain species of lactic acid bacteria that also have the ability to break down proteins. The souring of milk at the hands of lactic acid bacteria is one of humanity's great age-old traditions of preserving food, cheese making. And some of those lactic acid bacteria, like I said, also need other molecules from the environment, amino acids to build their own bodies. And when they work on not just sugars, like the sugars you find in milk, but the proteins, you get whole other flights of aromas and tastes being produced. And those are a lot of the tastes we associate with umami-rich cheeses. So, traditionally, classically, historically, people never really understood what was happening when they would make kimchi or make sauerkraut, or make sauerkraut berries, if you will. Historically, humans must have stumbled into this somehow. Now, it's great that humans have always lived on the coastlines. You could posit that just having access to salt water and maybe storing food in salt water was enough, given the salt content of the ocean in some parts of the world, sitting around 3.5%, almost in the sweet spot, was enough to actually kind of keep these foods safe, make that little makeshift brine, and allow these products to ferment. But these recipes were born of tradition and handed down for thousands of years before anyone ever had any sort of understanding about what a microbe was or why food went bad. But they knew through history, through tradition, through teachings of like grandmothers to mothers to daughters, that you could transform food and keep it safe just by adding a little bit of salt. They didn't have to know how it worked, but it was absolutely essential to their survival, to our survival as a species, that it did work. So these microbes have been growing alongside us, working in these very traditional recipes, sometimes being transferred from batch to batch to batch, And I guarantee you there's probably ferments out there that use a little bit of a previous batch back slopping to introduce these microbes into a fresh batch of a new ferment, whether it's kimchi or whether it's sauerkraut, what have you, that have been going on for thousands and thousands and thousands of generations. So we keep that lineage alive in this way. And fermentation goes really, really deep in history. It's something we've been doing since before recorded history. Some of the earliest recorded artifacts of fermented foods come from the Zargus Mountains, where people were where there's artifacts of people who were very clearly making wine in that region, purposefully with intent. So you have to think that just because you find that first artifact in a historical record dated, 8,500 years ago, you can't assume that it started at that moment. Obviously, this is a very advanced technology that people have probably been doing for much longer since even then. But we carry it with us today. We're talking about it. The world's best restaurants do it and serve these fermented products because they are recipes that are so ingrained in humanity's way of cooking and staying alive that they really have become inseparable. People talk about dogs being man's best friend, but you never think about the microorganisms that we've been carrying with us, traveling around the world with, and using in recipes that have been transferred between generations for thousands of years as being just as friendly and useful to humankind. So that's lactic acid fermentation. And like I said, there are these very traditional recipes that work because tradition is meant to keep ideas pure. The better your transmission, like a cultural mean from one generation to the next, the better you ensure the survival of whoever comes after you. If it kept you alive, if having cabbages soured for the winter was a way of making sure that you didn't starve in kind of the darkest months of the year, then tradition ensured that your children's generation and everyone who came after you would do the same. Tradition is about cultural mimetic fidelity. What Noma does is learns from that and then throws all that out by the wayside. You pick apart a process and you say, okay, well, if this works for cabbage and if this has worked for humans and cabbage for thousands of years, what about it works? Why is this so useful? And then when you ask yourselves those questions, you can then kind of extrapolate those answers and then apply them to completely different things and say, well, what if we fermented fruit instead of cucumbers or cabbage? What would that taste like? Would there be some sort of added benefit to that? And turns out there is. And so lactic acid fermentation at Restaurant Noma isn't so much about fermenting cabbages or traditional recipes. In fact, we've never served sauerkraut at Noma. It's often about the fermentation of fruit in an effort to kind of can the summer months when they're at their best, because Denmark does suffer through some very dark and dreary winters, so that we can have really delicious fruit for the winter menus and things like that. And just I'll speed through this and then come back. But this is what our lacto-fermentation room, which has a set temperature and set humidity, looks like in kind of peak season. And this is about 500 kilos of Mirabelle plums undergoing this fermentation process in vacuum bags to keep the air out, and salted at 2% to make sure that no malevolent bacteria can grow. Yeah, you have a question?
Yes, I just wanted to ask you how you then preserve it over the time, because if you leave it like at room temperature, it will keep on fermenting.
Yeah.
So you preserve it at a lower temperature, or?
Yes. So one interesting thing that you're going to realize about, or in this talk, is like, okay, well, you guys do these weird techniques that have kind of been not wishy-washy, but imperfect, that have served people for a really long time. At the same time, you're a restaurant that strives for 3 Michelin stars, or I mean, we have 2 now, but that's a different story. Or tries to be the best in the world. It works at an extremely high level. So how do you take something that is imperfect and often chaotic and up to organisms that you don't have direct control over and keep it exactly where it needs to be? And then there's a whole bunch of really kind of over-the-top things that we do at Noma to make sure that our fermented products are as perfect as they can be, which is a bit of a contradiction, so that the restaurant is consistent and good and recipes work. Now, if you ferment a plum, let's say, and it's in a good amount of brine and it has enough salt, you can technically leave it at room temperature indefinitely and like reach into that, and it's going to be extremely sour. It's going to change. It's going to start to, it'll get musty. Other things will start to break down in there if you give it enough time. But it is, in fact, safe to consume. And we've done it. You can leave fruit at room temperature for like a month, and it's still, you put it in your mouth like, oh wow, this is really sour. It's over fermented, but at the same time, it doesn't make you sick to eat it. The short answer, though, is that you use a cellar. And this actually works quite well in terms of the seasons and people doing this stuff traditionally. You think about it in South and North Korea, when grandmothers would make kimchi in the mountains, the harvest for that is in the fall. It rides out the last of those warm months, in October, November, in these urns that then get buried in the ground. And the ground keeps these things cold until the spring, when they can start harvesting new fresh vegetables and things like that. So by lowering the temperature, you kind of put a damper on all microbial activity. We'll talk about temperature in a bit as well. But that's the world of lactic acid fermentation. Yeah?
As you said, there are millions of different types of lacto-acid bacteria. Can you choose which ones you want to grow because they produce different kinds of metabolites, or just put salt in whichever grows? You can, but that requires a bit of microbiology. And that's not a bad thing. But when you take, let's say, cherries that were growing in the garden out back, and then you add your salt to it, you toss them around and say, okay, well, I'm going to start to ferment them. Into the jar they go. And you add a bit of weight on top to help it make that airtight environment. You can use fermentation weights. The plastic bag is kind of an easy trick that everyone can do. Just snap it shut, the gas can escape. What you're doing here, you're just taking whatever's in the environment. These microbes are everywhere. There is not a corner of the earth that does not have microorganisms in it or on it. And lactic acid bacteria are some of the most prevalent. They're already on the skins of the fruit waiting for the right opportunity to take hold. Yeast that would turn this into cherry wine are doing the same thing. They're already there, and they're opportunist organisms that are just waiting for the gunshot to go off to be like, oh, someone gave me the perfect environment, now I'm going to get to work. That's wild fermentation. There's no such thing as spontaneous fermentation. I hate that word because it harks back to Aristotle and his idea of spontaneous generation, which is completely ass backwards. But there's no such thing as spontaneous fermentation. The microbes were already there. You just set up conditions to let them flourish. You made a gateway. Your control points, that took all the microbes that were on that fruit anyway, blocked most of them, but then allowed certain ones to thrive. So if you want a specific taste or a specific kind of world of flavors in your ferment, you actually have to go and figure out which ones of these microbes are the ones responsible for those flavors, and then add them in a very sterile environment to make sure that only they and they alone grow. And that's kind of the world that industrial fermentation works in. When you are, a big corporation, when you're Dole or whatever, and you have to make 200,000 kilos of pickles for this month's quarter or whatever, you actually go to great lengths to ensure that your product is consistent and there's no other players in that board. So you'll almost sterilize the base products, wash them extremely thoroughly, sometimes irradiate them, whatever, and then add one specific microbe so that it has exactly that flavor. You have to inoculate that. You can't choose by temperature or something like that.
No, you have to inoculate. And it's not that you exactly have to sterilize, so long as you add enough inoculum, that one species will outcompete the rest. They'll get enough of a foothold that it'll just kind of quash the choir and then take over. So that's how big companies tailor very specific flavors of lactic acid fermentation in things like yogurt
or skyr, or lemon, or what have you. We actually have the good fortune of being in Copenhagen with Noma, alongside another very famous food company called Christian Hansen, which you might not have heard of, but this is a food company that is responsible for an enormous amount of the fermented foods you eat in the world. They are a microbiology lab that started with the fermentation of sausages in South America over 100 years ago, and then branched into every corner of microbiology in food. And they supply, if you buy yogurt in a grocery store, odds are they're the ones that gave that company the bacteria that they needed to make their yogurt.
What's their name again?
Christian Hansen. And they were kind enough to actually show us some of their processes. And so sometimes they'll find an interesting fermented product, bring it back to the laboratories, take samples, grow it on a petri dish, and they have the most insane machines that are like computer-controlled 3D printers, you know, dropping these individual swabs, if you will, onto a giant plate. They watch these things grow and then select and select and select and pare down those generations until they find the microbe that produces exactly the set of molecules that they want. And then they keep that as their kind of gold standard, grow it in quantity, and then that's their, you know, CHR 122.3 LAC. They give it some name, and then it's for sale for people to use. It has a very specific profile. Sometimes they'll make cocktails, and they'll take different bacteria that thrive at different times or produce different metabolites that work in concert to produce very specific flavor profiles. And it does get that fine-tuned in terms of tailoring. And you can do that, It's like breeding thoroughbred horses or dogs. You can make that perfect animal. But at the end of the day, a mutt's gonna love you and lick your face when you come home as much as like a $10,000 greyhound. So there's nothing wrong with wild fermentation, just understand that you have far less control than someone like Christian Hansen, who invests tens of millions of dollars to perfect genealogical lines to make sure that food tastes exactly how they want it to taste. It is a wholly other side of fermentation that is like science at its most extreme. Yeah. Next, are we good with lacto-fermentation? We get it, we understand? We're like, okay, now I get it. Yeah?
Can I ask how you can lacto-ferment like fruits without using salt if you want to keep back the sweetness, like using them as a sweet thing? Like, can you...
So, that's risky for the stated reason that if you do not have this control point, this line isn't here, and just everything's growing. You could technically try and add enough inoculum to like get it started. And lactic acid bacteria, like I said, they can tolerate salt. They don't need it to live. Lactic acid bacteria will grow even in the absence of salt. You can grow them on a petri dish, just in a neutral medium. But if you don't have salt, other stuff will grow too. So if you're trying to ferment, just kind of, you can't just leave fruit in a jar and leave it out on the counter and say, oh, this is going to lactose. That's rotting. You haven't added a control point. You haven't stood at the door with a velvet rope. You've just let everybody in. So you do need some salt. There are probably ways to do it if you add enough back slop. If you put it into an already fermented medium, it'll kind of just carry it along with it, hopefully safely, but that's no guarantee. You could maybe lower the pH enough, but then you're just pickling it at the outset and you're not actually fermenting it. So it's a bit risky. And another thing to think about is that this is, without the addition of salt, this is how you make wine. You just make an anaerobic environment, and the yeast will outcompete. Yeast is fast, and if there's enough sugar, the yeast will take off and you're just going to make wine. The only reason you're lacto-fermenting and not making booze when you do something like this is because you've added salt, and the salt inhibits the yeast and lets lactic acid bacteria thrive. Because the overlap in between what yeast needs to survive to produce alcohol and what lactic acid needs, or lactic acid bacteria needs to survive to produce pickles, is a fairly thin margin. So it's good to have control points. Yes, Professor.
Potassium chloride was working as well.
Potassium chloride.
Because
I don't know, I've never tried it.
No, because I think people use sodium because that it was what it was available. But since potassium, it will work anyway for the osmosis, but it will be much less salty.
Yeah, it's true. Yeah, I mean, people use it as a salt supplement. I don't know. Like I said, I've never tried
I was thinking now.
it. It's a possibility. But you also, like, maybe there's something about potassium ions that like mess up the metabolism.
Yeah, but probably it's because it's not available. I mean,
Yeah.
where you get it? I mean, now you can buy, but
Yeah,
the
exactly.
production is impossible.
You wouldn't
So probably
Yeah. That's good to think about. Cool. So that's lactic acid fermentation. Moving away from that, we're going to talk about kombucha. Yes, sir. Yeah.
Just a question for it about the cherries. If you know where to ferment them, wouldn't you be supposed to add some kind of a liquid or something to remove all of the oxygen? Or could you actually leave it like that?
If it's, I mean, this is just kind of a on-the-counter demo, but the thing about salt is that it's going to start pulling liquid out of those cherries. So you can take like a whole plant, and if it's not hardy enough, like there's probably dry packing carrots, big chunks of carrots probably wouldn't work because they're so sturdy and hardy that not a lot of juice is going to come out of them. Things like ripe fruits, the salt just by pressing them against the skin and being underweight is enough that it'll start taking liquid out of those out of the flesh of the cherries, and that's going to form the brine within a couple of days, which is a short enough amount of time that the fermentation process is going to get started.
That wouldn't be a problem for the bats, like, or allow the bat bacteria to grow.
No, it's usually enough time that it works out. You just want to make sure that there is enough weight. That's going to happen. If you don't pack it tightly, then it's just the salt's going to sit at the bottom. It's going to be a bit of juice there, and then it's going to run. And it's like one of the most common photos I get tagged in on this year. I'm like, how come this didn't work? And it's like there's no weight on top or whatever. You actually have to force the osmosis to take place. Just so you're aware. Okay, so kombucha. Getting into a different world of sour fermented products. Kombucha is traditionally a product of sour sweetened tea. It hails from Eastern Asia. Where exactly is kind of tough to say. Some folklore has it riding on the back of a Korean physician that would travel through Eastern China with this remedy being doled out to people who needed a little fixing. But at the same time, the bacteria and the microbes responsible for producing this do exist in the wild. There are little puddles that you see in the forests of Denmark that have something that looks like a SCOBY, that looks like a kombucha mother growing in it. And if you kind of stick your foot in or stick your finger in, it's like, oh, that's actually a little bit acidic. These are colonies of organisms that do live in the wild somewhere. Someone must have had the good fortune to have found one, put it to good use, and then kind of honed in or domesticated the things that it could do in order to make this a drink that everyone knows today. Can anyone tell me what kombucha, what it is, how it works? SCOBYs. What does SCOBY stand for?
Symbiotic community of bacteria.
Yes, exactly. So, I call it a colony, but potato, potato. Symbiotic colony of bacteria and yeast, a SCOBY. SCOBYs, in the world of fermentation, are kind of interesting because you can actually see them. When you lacto-ferment fruit, you never get to actually meet the people responsible. In a SCOBY, you can actually say, oh wow, this is what I'm working with. It looks kind of like an ugly jellyfish, so I don't have a photo of one. This is just the finished kombucha that you see on the screen. And it is this the symbiotic organism, if you will, a superorganism where yeast is operating on one level and then it's living alongside bacteria that then make what the yeast, or use what the yeast has produced, and then take it through to another process. So when we're talking about yeast working on fruit, turning sugars into alcohol, let's draw a little yeast molecule here. It's making a little baby budding. It takes glucose. That goes in, and then 2 molecules of ethanol come out. And then from there, acetic acid bacteria, a relative of lactic acid bacteria, but this time they have the ability to take ethanol and then transform it into acetic acid, take those and produce acetic acid as well. So when people talk about like fermentation pathways, this is why, because it actually looks like a whole set of steps, like an algorithm, if you will, that you're plotting on a whiteboard, of molecules being transformed at the hands of microbes into different products. So at each step in this process, the yeast is making ethanol and then garnering useful chemical energy so it can thrive and divide. This leftover then gets consumed by this microbe over here. Useful chemical energy is extracted. You can burn ethanol, right? That's chemical energy. It's basically doing the same thing inside its cells and produces acetic acid as a result. And it can thrive and survive. The acetic acid bacteria gets more out of this relationship than the yeast does, but at the same time, the yeast isn't much bothered by the fact that there's acetic acid living alongside it. The yeast that live in scobies can actually tolerate fairly high pHs. They've been trained to, just by nature of their environments, being so acidic all the time. But at the same time, you have to think that these are organisms that have made themselves useful to humans in the same way dogs have. Think about it. Wolves in the wilderness, a handful left. Tens of thousands, maybe. Dogs, millions on Earth. What's the only difference between wolves and dogs? One subset of this animal has made itself useful to humans, and being useful to humans is one of the most powerful evolutionary tricks animals, organisms on Earth have discovered to this date. If you're useful to humans, I can guarantee you we will breed you in great quantity. And that's exactly what takes place in a SCOBY. The yeast that gets to live alongside the acetic acid bacteria that produces this sour drink get to be very numerous and multiply. Their fitness is extremely high, if you want to talk about it genetically or evolutionarily, all because humans like to drink it. The domestication of any plant, of any animal, works for the organism that's being slaughtered or consumed because we grow it in the meantime before it dies in huge quantities. Michael Pollan talks about this a lot, but it is a fascinating kind of idea to wrap your head around. And this isn't the only place in nature where this happens, where humans directly affect their environment to grow a specific organism for their own benefit. Ants do it too. Ants are fermenters. Ants will, leafcutter ants, cut leaves, take them back to their lair, not to actually eat the leaves, but because a certain fungus grows on those leaves in the right conditions, and then the ants eat the fungus. So we're not the only animals in the world to ferment, and we're not the only animals to take microorganisms, domesticate them, and make them useful for our own purposes. In kombucha, the whole reason you can actually see it, these are microbes. You look at them floating around in a vat of water under a microscope, you'll just see little floaters. But the whole reason we can see kombucha as like a thing that you can transfer a mother into a fresh batch of sweetened tea to make it is because acetic acid also, in the process of consuming ethanol, produces cellulose that then forms what's called a zoogleel mat. Cellulose is buoyant, the cellulose that acetic acid bacteria excrete. So it floats to the top of this liquid and then allows this kind of mat or raft to form, which guarantees that all these bacteria and yeast that are actually kind of in this web of kind of organic matter get to be carried through to future generations. So it's made a very physical form to ensure that they always have a place to live and humans can take them with them. You can ferment kombucha with bacteria and yeast and make this kind of symbiotic colony without ever producing a raft if you're clever enough. But you also have to consider that there is, to these microorganisms, an evolutionary advantage to actually producing a physical form that humans can then be like, oh, I'm putting you here now. It'll always ensure that the lineage survives. That raft is also important, and the fact that it's buoyant is also important, because for acetic acid to actually run through this fermentation pathway, it needs oxygen. When you leave wine out, what happens? It turns into vinegar, right? Oxidized wine that's been open for a couple of days that the restaurant no longer wants to sell you. It's oxidized because oxygen is the molecule responsible for creating acids. That's literally what it means from the Greek, oxygen, acid former. And this was discovered by Lavoisier and others, over 100 or 200 years ago. When you oxidize ethanol, you end up with acetic acid. And while lactic acid bacteria are fine to work in the absence of oxygen, acetic acid bacteria need it to do what they do. If you put a cap on a kombucha, it'll just snuff itself out and die. You might get a little bit of alcohol fermentation, but there might be reasons why that doesn't happen. Kombucha needs access to oxygen in order to work. The oxygen is another vital component in this, and even in thinking about it that way, you also realize that adding an ingredient like oxygen is also a control point. Your batch of kombucha isn't going to work unless it has access to air, so that's why you keep kombucha covered with a cloth towel when you're fermenting it in a jar or a jug or something like that. That zoogliomat and its buoyancy ensures that those acetic acid bacteria are always in contact with the air, which is kind of neat. So they make themselves a raft so they can always have access to oxygen and then ferment the liquid. The liquid, just from Brownian motion, is always moving around in the jug, and eventually they'll come into contact with all the ethanol that's produced, and you'll get kombucha. So, kombucha isn't completely alcohol-free, even though this is kind of a lockstep process. Yeast is consuming the glucose that you've used to sweeten your tea, it's producing ethanol, then gets converted into acetic acid, but there is a little bit of lag time, and that's why you traditionally find that kombuchas have an alcohol content of 0.5 to 1%. So it's not technically alcohol-free. If you're serving it to children, be aware if they drink enough of it, they're going to go wild. And this is important because in contrast, we're going to talk about vinegar next, but in contrast with vinegar, vinegar tends to peter out for a couple reasons. Yeast, while they do produce ethanol and can tolerate it, how winemakers and beer makers control the alcohol content of their finished alcoholic beverage is by selecting yeast with certain tolerances to the amount of alcohol they produce. And this is a very seriously taken trick that yeast, or brewers, I guess that's what they're called, yeast makers, use to control very specific strains. So Chardonnay needs to be 12% alcohol, and all the sugar in the grapes will leave some behind because the yeast in that particular batch of wine will die off when the alcohol content of that batch of grapes reaches 12%. Alcohol is a poison, and it'll affect even the things that produce it if it's in high enough quantities. When you make vinegar, this process is divided, and this is why kombucha does taste a little bit different from vinegar. The yeast comes first, then the acetic acid bacteria come later. In kombucha, this cycle is constantly working. So the yeast never reach a high enough alcohol concentration because it's always being consumed by acetic acid bacteria being turned into acetic acid. So they never reach their threshold. So that being said, you'll notice something interesting about kombucha. You can run a kombucha completely dry and it will be extremely acidic because the yeast have never hit a threshold where they're going to die off from their own alcohol consumption. You can have kombuchas that are so far gone and so acidic that you would spit them out if you tasted a drop. And that's an important thing to understand, is that the fermentation of something like kombucha, where you have a set limited supply of some resource being transformed into two others, means that timing is an extremely important part of fermentation. Fermentation is cooking, it just happens more slowly. Do you have a question?
can we use this acidification of kombucha to produce something like vinegar? And to use
Absolutely, yeah. And some people use it as that. You can make a super sour kombucha. It's not technically a vinegar. It's just a very sour kombucha because you're gonna lose your sweetness. It'll just completely evaporate. All that sugar will be used up. And like cooking, good seasoning is all about balance. You can't add, a salad dressing is fat and acid and salt and other spices, and it has to sit in balance, otherwise it's not a good salad dressing and it's not going to be a good salad. The kombucha is the same thing. So while you're trying to achieve balance when you're whisking together your salad dressing, and it might take you 2 minutes to do that, when you're brewing a kombucha, you have sugar diminishing, while acid rises. And it's not exactly a one-to-one scale like this, but you have to understand that at some point in this chart, maybe around here, you're sitting in perfect balance. Maybe it's here, maybe it's here, maybe it's exactly here. But you have these windows where your kombucha is actually going to taste right. Now you also have to think about other parameters, like how much sugar did you start with to begin with? If you start here, compared to here, you'll have both more sugar and more acetic acid at the very end. So figuring out the right starting quantity, the right jumping off point for the amount of sugar in your tea before this whole process gets started is also extremely important to producing a kombucha that's well balanced. If you make a sugar syrup that sits at 25 bricks, that's 1/4 sugar, it's extremely sweet. The yeast can tolerate it, they'll start to ferment. But you also have to think that it'll produce a lot of acetic acid while there's still a lot of sugar left over. So you'll have something that's at once too sweet and too acidic, and it's not palatable. You have to find that sweet spot where there's an amount of sugar that kind of counteracts the acetic acid that's been produced, but there isn't so much that it's either too sweet or you give the bacteria too much fuel to produce too much acid. So it really is about kind of moving these triangles around and finding that perfect balance and perfect fit. So while this isn't like a perfect example of, like I haven't plotted this on Excel or anything, you can imagine that you could have very extreme charts where you have a lot of sugar and then a lot of acid being produced, and that kind of shape of that X being more extreme leads to a more unbalanced kombucha. So you want this kind of gentle curve, and you want to be able to hit that sweet spot. Just because you can fry something in a pan in 10 minutes time and say that you've cooked something, shouldn't put out of your head the fact that timing is also an extremely important thing in processes that take days or weeks or months. And that's what a good and diligent fermenter does. They understand the processes that are underway. They say, okay, well, I have X amount of time, I have X amount of days to make sure that I can see the rate of decline in the bricks. You can test it every day. And then ultimately you let taste be your guide. But at the moment where, okay, this is in balance, this is in harmony, you keep it there. Now to keep it there, you can either put something in the fridge, which again will slow down all microbial activity. It won't stop it. Stuff goes rotten in your fridge, you give it enough time, right? But it'll really slow it down. You could pasteurize your kombucha, but some people don't like doing that because they actually want to be taking in these living organisms and kind of bolstering their own gut with a healthy population that does their body good. Or you can freeze it. And so to get back to, I forget which young man asked the conversation or asked the question about like, oh, well, how do you keep it from getting too sour, over fermenting? This is how Noma does it. With kombucha, we freeze it because it's effervescent. The bacteria also produce CO2. CO2 gas. That's a bit fizzy and actually adds to the quality. So you can freeze CO2. You can freeze a carbonated beverage, take it out of the freezer. It's still carbonated at the end. So by freezing our kombucha, we make sure that it's exactly at that point. It's not moving around. And when we thaw it, we can use it. No detriment to the flavor. Still effervescent, still full of living bacteria. So it's a great way to do it. Not everyone has unlimited freezer space, not everyone would want to do that, but it is a great way to do it. For someone who's just brewing kombucha at home, if you want to make sure you're always drinking delicious kombucha, just brew it every week. It almost makes the process easier. Yes, sir?
Is the freezing bactericidal, or does it just...
No, absolutely not. It is not. there are certain instances, there are certain freezing techniques that will kill some bacteria, but a normal freezer in your home does not kill bacteria. It just renders them inert. So they stop working, they're locked in place, they're not moving around, and then everything stays there. There are ways to freeze things that will kill bacteria, but a -15 freezer that you get from the hardware store is just keeping things still. That's it. You can pull it out and then get the ferment going again if you really wanted to. So that's something to keep in mind. Kombucha is traditionally made of tea, of black tea. Oh, a lot of questions. Okay, before I get into that. Yep, you in the back?
Have you ever tried to make kombucha with something different from tea?
That's exactly what I was going to start talking about, so I'll start talking about it in a second. And then another question?
Can I restart a SCOBY from, like, let's say, a 2-year-old acidic bottle of kombucha?
You can try.
Okay.
It might work. The bacteria might be in stasis. I would say that's pretty risky. To me, that's like bad news bears, like it's gonna just not work, or something else will be in there. But it's possible that they're still alive and still okay. Bacteria can survive in stasis for a very, very long time. And you'd be surprised with, you know, you find spores of koji, which we'll talk about in a second, that can just live on a shelf for years. So some of the most indestructible mushroom spores and fungal spores are some of the most indestructible cellular generational propagators you can find, and they can like survive the vacuum of space, come back down to Earth to survive being irradiated, and still grow. So there's some instances where, yeah, you can take something extremely old or something you've forgotten about and get it going again, but I'm not saying it's guaranteed. It might just not work, or it might be off, or maybe the yeast have died, but the acetic acid bacteria are still alive, and then it's just all wonky. So to answer that question, when I said the easiest thing to do for you is to just make your kombucha fresh every week, that is the answer. If you always have a batch of kombucha going, your SCOBY will always be healthy. You have to feed your dog to keep it alive. You have to feed your kombucha mother to keep it going and keep it healthy and keep it strong. Now, as it grows, it makes more of itself. Bacteria are always constantly dividing by 2 by the process of mitosis. So you've got to think that, yeah, if you have a little bit extra, give it to your friends and then spread the joy. But that is really the easiest way. If you're pulling off a kombucha, just brew up another batch, backslop, add a little bit of that previous batch in to just lower the pH to make it a little bit safer for that batch of kombucha to get going. And then from there, just let it go for another week, and you have your kombucha for the week. You stick it in the fridge or put it in bottles or whatever and take it with you to lunch. So yeah. So yes, to answer your question in the back, you can make kombucha out of different things, and that's exactly what Noma does. Again, we look to tradition and say, well, why does it have to be this way? So traditionally, it's made of sweetened tea, like sugar cane sugar into black tea, add your kombucha, and let it ferment. But at Noma, we found that you can ferment a whole lot of other things. And so yes, there are some pathways, there are some sugars that yeast can't ferment. If sugar chains are too long, yeast enzymes won't work on it, it won't be able to break it down. But there are a lot of sugars that work completely fine. And a lot of fruit sugars, fructose, disaccharides, things like that, maltose, are completely fermentable by the yeast that live in kombucha. And that's something we discovered quite early on. One of the first kombuchas that Noma ever made was a carrot kombucha. Carrot juice is extremely sweet, normally sitting at a Brix of like 12 or 14. And that's kind of in that perfect range, that perfect sweet spot to make a really delicious and great kombucha. And that was one of the first non-traditional kombuchas Noma made, and it works great. I see a lot of people like commenting on the book, complaining like, oh no, but you need tea, it needs like certain antioxidants, it needs this molecule, it needs that molecule. That's all well in theory, but if you do it and it works, then so much for the conjecture. And so we do that at Noma a lot. We brew kombucha from fruit juices, apple juice, berry juice, blackcurrant juice, pear juice. We've made it from asparagus juice. Sometimes you have to add sugar to actually sweeten it to the right level. Sometimes you can just use the natural fruit sugars that are in there and allow it to go. You can make it from honey, which is one that a lot of people think you can't, because honey sugar molecules are actually a lot larger than just say white table sugar. So yeah, it is kind of this world of exploration. You'll find that not everything works, but a lot of stuff does. So that's kind of the joy of it and how you have fun. Yeah.
Have you ever tried to use like wine or beer must?
Wine or beer must. Wait, so like, yeah, no, yeah, you could absolutely do that. But the must after it's been fermented into wine, if it's like alcoholic, it's not gonna.
No, it's just grape rest, so it contains sugar, but that doesn't contain alcohol.
Oh, okay, before it's fermented. Yeah, you could absolutely do that. Again, you have to make sure that you water it down and make sure that the sugar content is sitting at the right point. And you do that by just getting a refractometer and kind of looking to the stars and making sure that the sugar level is exactly what it needs to be, but it would absolutely work. We don't have grapes in Denmark. It's too cold, so we don't make grape kombucha, but I imagine it's delicious. That's the other thing about the Noma Guide to Fermentation. If there was like 10 Nomas all over the world, in every corner and climate, this would be a much larger book and we would have tried everything. But we're also restricted by our mandate to kind of cook within our region. So this book is kind of dedicated to things that grow at northern latitudes, which again, there's a lot of overlap with other places on Earth, but grapes, unfortunately, not one of them.
So did you try the coffee?
Yeah, we make coffee kombucha, and it's absolutely delicious. And we actually make it from like our leftover coffee grounds that we use for the guests. We just do a second cold steeping. We add sugar to it, and then ferment it, and it's absolutely fantastic. It's so delicious. People love it. It's like people ask, oh, you must be so full of fermented. It's not like I'm working at Nome and like snacking on the koji all day. I'm a bit sick of it. But the one thing, if we're making it for the menu that I do enjoy, is the coffee kombucha. And we've done so many trials. We've done so many tests, so many different varieties, concentrations, levels. And that's the other side of it, is that fermentation is this kind of, it is as large as the world of cooking is. So in every way you could imagine making a soup, in every, okay, how many carrots? What's the ratio of carrots to onions to celery? How many different varieties of soup can we make? And what will they all taste like? You can have a sensory analysis afterwards and say, this is the best soup. That's what Campbell's should do. You can do the same thing in the world of fermentation. You can make 100 different flights, different increments, using different bacteria, using different sugar contents, and then find that perfect sweet spot or that perfect kombucha that you can then serve to all of your welcome guests. Yes?
Question about, does the SCOBY create any, side molecules that give another flavor except of the acetic acid and the ethanol? Are there any?
Yes, they do. Like I said, the drawings on this board are fairly simplistic. But if you find a research paper, and I've read through a fair bit of them for other reasons, you'll find that people who do analysis, who run analysis, okay, what's actually going on in the SCOBY? There are a whole other bunch of volatile aromas and chemicals being produced. Life is not simple. Even simple life. I love it when biologists are oh, for 2.5 billion years, simple life. Very simple organisms are not simple. It is incredibly complex the way that they treat molecules, the enzymes that they use to thrive on Earth, and they will produce whole different flights of molecules as a result of their living that then affect the finished product. It's not just black and white. It's not like two things are being produced. It's more than that. But these are the ones you have to kind of pay attention to.
What are you then using it for in the restaurant as a kind of complement to solid food, or are you using
so if you come to Noma,
for the preparation of solid food?
Both. If you come to Noma, and Noma has no hard or fast or set rules about how it cooks with food. If we want to pickle something, we'll pickle it. If we want to make an ice out of a kombucha, we'll do that. If we want to serve someone a drink, we'll do that. So kombucha is used a lot as an alternative to the alcoholic menu, even though, yes, it has 0.5%. We're normally mixing it with maybe a little bit of fresh tea or another fruit juice and making up basically a non-alcoholic or a very low alcohol cocktail. And if you come to Noma and you're pregnant or you don't want to drink or you're Muslim or whatever, you can order the juice menu and have kombuchas that are very fancifully made out of very expensive ingredients. This is Saffron Kombucha, which is our inventory chef really does not like it because it kills the food cost, because I throw in 100 grams of saffron into a 25-liter bucket and I'm there's €100. So, and it's just for a drink that people consume. You can reduce kombucha to a syrup, so it's sweet and sour, almost like a gastrique. But of course, with all of the added benefit of not just being wine and sugar, or wine vinegar and sugar, but it's like, oh, you get all this fruit flavor with it. You can make a strawberry kombucha gastrique and dress strawberries with it, or strawberry sorbet, and it's like, because you have all of these layers of complexity of the same flavors kind of being stacked on top of each other. So there's really no limit to how you cook with it. You can treat it as a drink, but you can also treat it as an ingredient. It's just, you're limited by your own imagination.
Okay, is there a limit to viscosity or thickness of the liquid for it to work?
You would think so, but then in this book, while we were in Mexico, that was something I was kind of, Mexico, hot place, people really like to cool down, so this is mango kombucha, and I was like, well, why couldn't it work? Like, the fiber's not going to go anywhere, the fiber's just going to stay there, and it's not like it's going to inhibit the bacteria from getting the glucose. So, yeah, this is like a thick puree. It was like Mexican mangoes, blended in a Thermomix, and then fermented. The problem is that, first of all, you'll get like a little bit of a phase separation. You'll have a bit of the pulp on top, where the SCOBY's sitting, and then a little bit of more liquid underneath. But the viscosity was not an inhibitor at all. So yeah, of course you can't just throw it onto chopped fruit and be like, ferment into kombucha. It's not going to work. It needs to be a liquid. But that was a very thick puree, and it worked fantastic. And the finished product was amazing, because you had this basically kombucha smoothie. So you can do it with other fruits as well. You just have to be sure to stir it every day to make sure that all of those molecules are moving around, and then keep the kombucha mother kind of well moistened by just ladling some on top. So it'd take a little bit more work, but it'll still function completely fine. Yeah?
Does people use the SCOBY itself in any other purpose, which like fry it or candy it or whatever?
Sorry, say that again?
The SCOBY itself,
yeah.
Would you use it in any other ways?
Yes, you can. I've seen, one of my interns actually kind of took on a project and was like, oh, I'm going to make this taste, and I'm like, you can't. I tried. But he actually just boiled a thick SCOBY down in sugar syrup, like basically candied it. And it was okay. It kind of tasted like a wine gum, but with the syrup in it, and it's wet and it's moist. But it was actually like palatable. It was good. Like Mugaritz is famous because they serve people live SCOBY, and I'm like, it's not good. Like I've eaten Mugaritz and they're amazing. They're like to me it's like Noma and Mugaritz. It's like, wow, cool restaurants on earth. But sometimes they do stuff that's not delicious for the sake of doing it. They serve people SCOBYs, and I've tasted some of them and it's like, oh, you don't need this. The cellulose itself has no flavor, and it has the texture of like placenta. So it's not, at some point you're just doing it to do it. I've seen people make like leather out of kombucha SCOBYs and stuff, and that's fine. If you're like gonna wear it, you can make art from it, do all sorts of things, but I am not a fan of eating it. There's absolutely nothing wrong with you eating it. It's nothing but pure fiber, but the texture is terrible. It doesn't yield there. Anyway. Yeah, you, sir.
I just wanted to know if the light and temperature is important in the brewing.
Light. So, light and ferments. General rule of thumb, don't leave your ferments like in direct sunlight. Ultraviolet radiation is antimicrobial. Because you're taking light waves, super energetic photons, particles, and you're just busting up DNA. That's what skin cancer is. It's sunlight busting up your DNA, it goes haywire, your cells die, or they reproduce without end. So yeah, UV radiation, bad for life. All life. Some life can tolerate it, but generally leave it out of the sun. The light from an LED isn't going to do anything. I don't notice a difference when our kombuchas are fermented in the dark or the light. I haven't done like super controlled tests, but some days the light in the room is off. Kombucha works just fine, some days it's on. The kombucha works just fine. Temperature is also a super important feature in all forms of fermentation. Like I said, if you want to slow a fermentation down, if you want to dampen those microbial processes, you lower the temperature. What's temperature? Basic grade 9 physics. Come on, what's temperature? It's energy of molecules. So yeah, it's the kinetic energy, is the average kinetic energy of molecules. And if microbes need to actually bump into all these molecules to be able to grab onto them to ferment them, the faster those molecules are moving around in a liquid, the more those interactions are going to take place. So when you cool something down, you are literally slowing down the kinetic energy of all the contents of whatever's in your vessel. So that includes the microbes, it includes all the molecules of glucose, it includes all the molecules of ethanol that are produced. The warmer something is, the faster it will ferment. Now there are limits. Just like you would no doubt die in the Gobi Desert on a hot summer day if you stayed there for too long in 45-degree heat. So too will microbes. They all have their threshold where things no longer work. Most life on Earth can't survive above 60, 62 degrees Celsius. That's like really the kind of the line. There are thermophiles or extremophile bacteria that do thrive in extremely hot environments. As far as I know, none of them are used for fermentation or produce useful fermented metabolites, so forget about that. But generally, room temperature or slightly above, up to 28 degrees, is a fantastic range in which to ferment products with bacteria. And those are called mesophilic bacteria, or middle level, which means just basically they like the ambient temperature. Other times, if bacteria get a little bit overheated, other fermentation pathways will come into effect that normally wouldn't be in place at a lower temperature, and sometimes you can get off flavors. So sometimes you'll be speeding up other reactions that wouldn't normally take place at lower temperatures, and you'll notice if a kombucha is fermented in like 30 or 35 degree heat, it'll taste a bit weird. Other things are going to start happening. No, I can't get into the specifics of which reactions, but you just know from experience that okay, you get off flavors if you ferment too high. Too cold, that's less of a problem, but it just does take a very long time. You can throw a SCOBY into your sweetened tea and put it in the fridge and wait a month and you'll get kombucha. But why would you want to wait a month for something you can do in 6 days? So that's the idea there. Yes, Sean?
What's the difference between a vinegar mother and a SCOBY?
Okay, yes. So this acetic acid bacteria, this is the guy in kombucha that's responsible for producing that zooglial matter. And like you see, ETOH, acetic acid, oxygen, you get your mat. In a kombucha mat, the yeast are living in here as well. So like everything goes along for the ride. Even the flavor of the base of your product is in the mat. It's basically a giant sponge. Layers of cellulose that are kind of stacked on top of each other, everything goes with it. And that's how the kombucha propagates effectively. In a vinegar mother, the yeast isn't present. Like I talked about, vinegar, two-stage process. First, you make wine, the yeast die off, then you introduce acetic acid bacteria, they do their thing. You can find acetic acid bacteria that still produce this zooglial mat in absence of yeast, and that's what a vinegar mother is. So a vinegar mother is basically this mat just without the yeast. And so when you see vinegar floaties, just understand that it's the same bacteria, the same family of bacteria that are responsible for producing the same thing in both SCOBYs, kombucha SCOBYs, and vinegar mothers.
So if I would take a vinegar mother and put it in a kombucha, would it become vinegar or would it just become very acidic kombucha?
So if you take a vinegar and put it into like a kombucha base, like sweet tea,
or that's already made, it's halfway, let's say. You put the kombucha.
Maybe it's possible that you could start making this hybrid organism and the yeast would end up living. It's possible. It's plausible. It's plausible that the yeast would then start occupying alongside what you took out of your vinegar mother. But there are vinegar mothers where if you just took that vinegar mother and threw it into sweetened tea, nothing would happen. Because those acetic acid bacteria have no way of breaking down the glucose. There are certain, life is very diverse and there's no one catch-all for how all this shit works. But there are acetic acid bacteria that can metabolize glucose and then just straight make acetic acid. And so sometimes you'll find a vinegar mother where it's just like, oh, you can just throw it in and then you get vinegar. But it is a little bit different. But this is the broad and kind of most correct and easily definable way of thinking about both kombucha and vinegar.
If I don't have a vinegar mother, can I use a bit of like my SCOBY in the kombucha, and because of the lack of sugar and presence of ethanol,
It should. It would ferment because the acetic acid bacteria will still be able to thrive in the alcohol. And it would take over.
Completely die off, or like?
It's possible. It's possible. If the yeast in that kombucha mother can tolerate whatever the alcohol, if it's beer and you're trying to make a malt vinegar, probably 5% is okay. It's not going to kill it. Maybe if it's like if you're trying to turn soju into vinegar, you might kill everything. So just think about that. And again, you never know until you try. This is like Noma has done a lot of work in the world of fermentation, but at the end of the day, we don't have a microbiology lab. I can't send, I don't have a budget to be like, oh, I just really want to know what's in this batch of kombucha today, even though I have 10 others on the go. I don't get to send that away to a lab to say what exactly is growing, do a DNA analysis, tell me exactly what metabolites are in there. It's extremely expensive. To be able to understand, like, bottom line, what's actually going on in that vat, you need to look at it with very expensive machinery and run assays and spend a very highly trained person's time. So at the end of the day, we're still cooks. We turn to science to be able to do this, but to really know, we just taste and use our tongues. And if it doesn't work, then it doesn't work. And then you learn and you go from there. So a lot of it is, understanding the science, but at the end of the day, we try it out. And if we run into an experiment like that, we literally say, okay, do 2, and then if one dies, then we know what it was, and then if the other doesn't, great. So yeah. Yes, sir? Yeah.
Can you just move your SCOBY around from one liquid to another, or you have to adapt it slowly to new kinds of...
No, you can move it, but it's up to what you want out of it. From the microbes' point of view, they're happy to live in whatever environment they're thrown into. But if you just take a SCOBY out of black garlic kombucha and then throw it into your banana kombucha, I'm not going to say that's going to taste good at the end, because it's tainted. You wash your cutting board in between working from chicken and lettuce, so why not do the same for your SCOBY? So the easiest thing to do is just divide, and then just keep those lineages going strong in whatever mediums they're working in. And sometimes that works to your benefit too, because sometimes, as in the case with saffron kombucha, there might be certain organic molecules that are actually antimicrobial, that then you've created an evolutionary pressure for all of these microbes to work around. There's a little anecdote in the book about me doing black garlic kombucha for the first time, using all the leftover skins, steeping those to get all the sugars out of them. These now caramelized and broken down and pyrolized sugars. It tasted great, the base syrup, but the first kombucha took 3 weeks to get going, and I thought it was dead. And it was all because the alinicin in the black garlic was actually hampering the yeast, until enough of it divided where one that was a bit tolerant to alinicin could thrive, and then from there, you now have a black garlic that, it's evolution in real time. It's breeding. It's like selecting the smallest dog to make a chihuahua. You make something very specific given the parameters. Yeah, cool. Kombucha. We're good. Next, which is fairly simple, but vinegar. So, as I explained, vinegar is a 2-step process. You take your grapes. That's what grapes look like. You add yeast. And those grapes get turned into wine. Should have become a painter. After the yeast produces, let's say, well, whatever that yeast can tolerate in terms of alcohol, let's say 12% alcohol, it dies off. See you later, never to come back. It shrivels up, alcohol poisons it. There's an interesting allegory here for humans on Earth and like global warming and like what yeast does to kill itself off when conditions get too good, but we're not going to get into that. This is for philosophy class. So the yeast dies off, and then you introduce acetic acid bacteria. Now, acetic acid bacteria is everywhere. It travels on dust molecules. It is an extremely prevalent type of life on Earth. Again, they often live on the skins of fruits, waiting for that opportunistic moment where they can thrive. But if you introduce them on purpose by either backslopping with a little bit of old vinegar, you will then let those acetic acid bacteria And you have to take the cork out of the wine, and you'll let those acetic acid bacteria turn that wine into vinegar. That's a vinegar gel. So that's the important distinction here. So we have 2 steps. First yeast, then acetic acid bacteria. So they're clearly delineated. And the important thing about this to note is that in the same way that vinegar or winemakers, beer makers, whatever, control the dryness of their wine by testing the Brix of the juice at the start, selecting a strain of yeast that will leave a specific amount of sugar left afterwards, after the fermentation is complete, and they can control the actual flavor of the wine that way. So too are you effectively controlling the flavor of whatever vinegar comes in its place. The acetic acid bacteria will only work on the alcohol, and again, cooking is balance. So if you have a very dry wine, you will get a very dry vinegar, and it's going to be a vinegar that doesn't actually taste all that good. A vinegar should also be balanced in terms of sweetness of the residual fruit sugars mingling with the acetic acid that you then produce. So that's the basic process. We kind of touched. There's a lot of analogies with kombucha here. But an important thing to note is that yes, oxygen is a very important thing to consider. You need access to oxygen to be able to transform a molecule of ethanol into a molecule of acetic acid. Oxygen, the acid former, the entire act of oxygen is an extremely reactive molecule, O2 is. It's a reactive atom. So 1, 2, and then it's hungry, so 1, 2, 3, 4, 5, 6. And it just loves stripping electrons into its sphere. So it's really greedy. And that's the whole point. And that's why it's an acid former. The oxidation of iron into rust, oxygen being greedy. The oxidation of ethanol into acetic acid, oxygen being greedy once again. So it's a greedy molecule. And this is something to keep in mind because you can use that to your advantage. If you want to speed up the process of making vinegar, which is technically quite passive, if you just let wild acetic acid turn your wine into vinegar, you'll wait a couple months, but it will happen. Those bacteria will just float on in. The wine will eventually sour, but you're not doing much to facilitate that speeding up. You can make vinegar that way, but you can also speed up that process by actively aerating your wine. The more oxygen the bacteria have access to, instead of just being in contact with a narrow surface area at the top of a jar, the faster they will metabolize ethanol. So at Noma, what we do if we want to make a vinegar very quickly, if we're trying to preserve the fresh flavor of a fruit or vegetable juice, we will aerate our vat of base with a fish pump, like literally a fish bubbler. You know, something that you'd use in a fish tank, and then out come all the bubbles. And that's a really clever technique because the air stone sits at the bottom of your container. If you have a very tall vessel, it's bubbling oxygen from the bottom to the top. It's actually making a circulation flow inside that vat. So all of the bacteria that are then living inside your alcoholic beverage to be turned into vinegar are always in contact with oxygen, and they're always producing acetic acid. So a process that would sometimes take 1 or 2 or 3 months can then be shortened down into 10 or 14 days. Now another really fun, kind of just clever thing that we do at Noma is to turn juices that would normally not ferment into wine into a product that can be fermented by acetic acid bacteria. And we do this by cheating. We just add pure neutral grain spirit or pure distilled alcohol. If you think that these guys need that alcohol to be there to do what they need to do, that doesn't preclude the fact that that alcohol can come from a bunch of different sources. It doesn't just have to be produced by the yeast that was living on those grapes. It can come from other places as well. You actually need a fair bit of sugar. Grapes are very sweet and have a lot of sugar in them. And to produce something with an alcohol content of 12 Brix, you need sugar contents of like up to 18, 20 Brix to be able to produce that much alcohol in your finished product. If you want to make vinegar out of celery juice, celery, not so sweet. You could try adding sugar to it, but then you're going to get into a whole mess of other problems. So what we do is we'll take fresh celery juice, the juices of a lot of different plants and vegetables, rhubarb, squash, pumpkin, things that aren't normally fermentable. You can ferment water into vinegar if you wanted to by making this, by using this step. So you take your pure 96% ethanol, not denatured, because that has other harmful things that'll make you go blind in it. You pour it into your vat at around 8% concentration. And then you end up with, then you just pick up this stage over here, you add your bubbler, you add your acetic acid bacteria by backslopping, and then this will transform, it'll completely be used up, your juice will no longer be alcoholic, and you will have a vinegar juice that's sitting at around 5%, 6% acetic acid by weight. Yes, sir?
So you would, to add the acetic acid bacteria, you would then just add a part of vinegar?
Yeah, that's the whole process of backslopping.
And
so,
does it matter what type of vinegar you use?
No, it does, because whatever you're adding is going to flavor.
Yes, but apart from that?
Apart from that, you just need the bacteria. You can get freeze-dried cultures of acetic acid bacteria and just use that if you want. They're very hard to find. It's not as easy as finding lactic acid bacteria for making yogurt, but they exist. But for the most part, vinegar making is made by backslopping. So if you have an unpasteurized, what's it called in the States, the apple cider vinegar, all the hippies drink. You have that, you throw it in, whatever, 10%, 15%. That's going to be enough of that bacterial culture to get that next batch going. It's going to flavor your vinegar, but then that just gives you a reason to do it again. So let's say you're making celery vinegar, and the first stage it's like celery slight apple vinegar because you backslopped. You do it again, you use that celery vinegar, and then you're diminishing the quantity of that original flavor each time until you have a very pure celery vinegar that you can use as backslop for celery vinegar that has a healthy population of bacteria in it. And you have a very pure celery vinegar. So that's the idea with that. I have to move through a lot of material now, so are we good on vinegar? We don't have to talk about balsamic wine or balsamic, you guys live in Italy, so I'm sure you get enough of that. You don't need to hear it from me. Okay, cool. So, yeah, you can make vinegar from a whole lot of other things other than necessarily grapes. And that's really where you do run into a lot of delicious flavors. When you turn things that would normally not be fermentable into wine, into vinegar, you can then use them to dress salads and things like that. And you're like, oh wow, like a lettuce vinegar or a lovage vinegar. And you get all these amazing floral notes and herbaceous notes into a product that you wouldn't be able to do just by steeping. And doing a vinegar this way does make it taste different than just like taking a finished white wine vinegar and blending in your herb. It does not taste the same. It actually goes through a process. Like I said, none of these processes are black and white. None of these processes are A goes to B goes to C. There's a lot of other things that get carried along in the flight, and you get complexity of flavor when that happens. Cool. See you later, vinegar. So now we're going to get into a very important ferment at restaurant Noma. Koji. This is Yu Ting, who was my intern last year. She was lovely. Making koji in the lab. Anybody tell me what koji is before we get into it? Shout it out. Who knows? No one knows. It's a fungus. Yes, you're absolutely right. Anything else? There's lots of fungus. There's mushrooms outside. It's more than that. Nada? Nothing? No. Okay. Koji. Before we talk about koji, we're going to get sidetracked and talk about beer. There's no recipe for beer in this book because Noma doesn't produce its own alcohol. We don't have a license for that, so we don't do it in the fermentation. We have done it in the fermentation lab, but we don't do it, so I didn't include it. But it is very important to talk about beer, because in talking about beer, we talk about grains. And the substrate, the thing you're looking to ferment, is sometimes as important to the ferment as the microbe you use to ferment it. What are grains? What are they? Seeds. They're seeds. Seeds are, what are seeds?
starch.
Yeah, there's starch in seeds. That's a component. I wouldn't say that's what they are. So we've got one component, starch, that's this. What else is in seed?
Proteins and
There's fiber. Where's the fiber in the seed?
Outside.
Husk, yeah, cool. So we got that. So we have fiber, the husk. What else do we have in a seed? Carbohydrates, that's the starch.
The germ.
The germ. Very important. Those are, for all intents and purposes, the three most important parts of a seed. What's the germ? Can we give that?
It's a small plant.
It's the small plant. There we go, that's what I was looking for. A seed is a baby plant packed with its lunch to take to school by its mom, wrapped up in a lunchbox. That's what it is. That's a seed. That's all seeds. When a grass produces a seed, it's putting forth its next generation. It is investing a lot of its energy to produce the next generation, all that DNA, that package, that first embryo, and giving it, again, a very costly form of food, a food source, so that when it starts its life, it'll have something to work with. You can't just throw genetic information into the wild and expect to make a new organism. You can't just throw a human embryo, fertilized with sperm, into a field and be like, make a baby. You need to actually nurture it. And plants nurture their offspring by making this very ingenious setup. Seeds are some of the most fascinating biological objects in the natural world. They are the genetic information for a baby plant packed up with the food it needs to start its life, wrapped up in a hard-to-get-at husk. Baby plant, lunch, in a lunchbox. Out into the world, be fruitful and multiply. When conditions are just right, genetic material inside that germ starts releasing enzymes that break down the starch. What's starch?
Sugar.
Kind of. Complex sugars. So, now, I'm no Professor Marini, I can't draw these molecules exactly perfectly. We'll simplify it and just say that it's a chain link. In starch, you have long connected chains of sugar molecules. Let's say each one of these is glucose. And they're linked together. And you form, glucose is a saccharide, a sugar. You form a polysaccharide. This is hard to digest. And it's built that way on purpose. Starch is made to be hard to get at, so it's not just freely consumable by whatever organism might happen to come upon it. Energy can neither be created nor destroyed. Law of conservation runs the universe, that law. And for a plant to make an energy-rich molecule, it takes a lot of work. It takes a lot of sunlight. It takes a lot of water for a plant to make glucose. It is a precious molecule, and that's why so many things on Earth seek it as their fuel source. When a plant invests all that time and energy in making starch, it wants to make sure that it's not just freely accessible to anyone. It has to keep it safe. So putting glucose molecules together in a long link makes it hard to digest. Big things are kind of hard to fit in your mouth, if you will. And they're not just freely available for anything that might float on down to start consuming. To make sure that this baby plant can actually get at its lunch and enjoy it, to take that lunch out of its wrapper, that plant has enzymes that can break apart these long chains of molecules and get at these individual molecules of glucose that it can then break down and use for its own life cycle, just like the bacteria, just like the yeast. What are enzymes?
Proteins.
They are proteins. This is very true. Beyond that,
reactions.
they are, maybe you said catalysts, or maybe I just heard that, but that's what they are. Yes, they are proteins that serve as catalysts for chemical reactions. In layman's terms, they are both keys and scissors. The way that proteins can fold and form extremely complex three-dimensional shapes, and then by the grace of the laws of chemistry, you can do really cool things with electric potentials at active sites that make enzymes extremely well tailored at doing one thing and one thing. Sometimes you have enzymes that do more than one thing, that you have enzymes that do one thing and one thing really, really well. They are this complex three-dimensional key that only works, in some instances, at breaking apart a molecule, a polysaccharide of starch, into a disaccharide of, let's say, maltose, which is easily digestible by a lot of animals and plants, by cutting it at every 2 molecules of glucose. So in some ways they're keys. And this only works because beta amylase, the enzyme responsible for doing this in a plant, has a very specific shape, just like a key. But then this isn't a key that just opens a door, it's a key that breaks apart material. So it's keys and scissors. Specialized, tailored shape, breaks apart molecules. Keys and scissors. That's what enzymes are in the world of fermentation. So, this germ, this baby plant, has been equipped by its mom with the keys it needs to unlock its lunch. And it prevents outside organisms, whether that's bacteria or birds or whatever, from getting in by creating this hard shell of fiber. A very hard to break apart organic molecules that make this hard shell. And when conditions are just right, this germ can consume all this starch, sprout its how do you say that word again? Cotyledon? Whatever, the baby plant leaf. And then the plant can start its life, put up its first sprout, start photosynthesizing, and on it goes. The circle of life continues. Everyone saw The Lion King. So, this is cool. This, life is fascinating. We actually get into how biology works and how things on the earth live and do their thing and thrive and multiply. This is cool. Now, in fermentation, like I said, it's not just about microbes and your base product, it's also about human intent. And thousands of years ago in Mesopotamia, the ancient Egyptians and Iranians and everyone living in the Fertile Crescent discovered that sprouted grains can make a really, really delicious alcoholic beverage called beer. How do they do that? If the yeast can't break down starch when it's in this polysaccharide state, well, they do that by tricking the plant into starting its life cycle and breaking down those starches into sugars for them. But before all those sugars are used up and it's sprouted its first leaf, you kill it. You kill it by roasting it. Does anyone know what process I'm describing? What is it?
Malting.
Malting, exactly. So, by malting a grain, you're getting the plant to produce enzymes that can break down the starch to produce sugars that you can then roast to kill the plant, to stop the process, halt it in its place, and all of those roasted sugars are now extractable when you boil them in water. If you were to just boil unmalted grains in water, what do? You get porridge. That's not exactly something you can turn into beer. If you boil malted grains in water, you get a wort, which is fermentable by yeast, which you can then have, a frat night, go to town, get drunk, whatever. We understand beer. Not necessarily important to Noma, but the idea behind this process is very important to all of fermentation in East Asia. So in the West, thousands of years ago, our ancient ancestors might have discovered the process of malting, all well and good. That leads to beer, that leads to malt vinegar, that leads to whiskey and scotch, and that whole world of fermentation. In East Asia, that never occurred to anyone, or it came too late because they found something else. They found a fungus that can do this for them. And it was a wild crop fungus. It was actually a parasitic fungus that would parasitize rice fields, rice paddies, and take this valuable starch for itself. Just like a fox gets into a chicken coop and takes those chickens for itself, so too does Aspergillus oryzae, I'm not going to write that, take the starch that someone worked very hard to produce, whether it was a wild plant or a farmer in his field, for itself. Crop funguses are one of the most, biggest pestilences to farmers and growers of food in the world. Funguses are some of plants' biggest predators. They might not look like it, but they are. So, once upon a time, some very adventurous culinarian, or someone just plain out of their mind, decided that they would take some of this moldy rice in a field and try and do something with it. And lo and behold, they found that this same process of malting was effectively taking place in in the rice that was infected with this mold. You could then steep that rice, that moldy rice, into a liquid and find that the rice got a lot sweeter. You could add unmoldy rice into that, and all of those enzymes that were produced by this parasitic fungus that hacked those grains' own life cycles and produced the same enzyme so that it could fuel its life cycle, those would go to work on other unfermented grains as well. And thus the process of rice wine, or sake making, was born. And this is where it comes from. It was a wild crop fungus that was then domesticated. People found this to be useful, and then they started doing it on purpose. It first started in ancient China, and the first records of it go back to, the time of Jesus, 50, 100 BC. And then from there it got carried into Japan, and Japan being so otaku, were like, oh no, we're gonna get really nerdy with this. And then bore the whole world of sake and all of the tens of thousands of domesticated and different species of Aspergillus oryzae we have today. So koji was a once wild crop fungus that often produced, like we talked about with lactic acid bacteria, metabolites that were harmful to people. But we slowly bred it and bred it and bred it and devised ways to kind of narrow in. We kept out the harmful batches, just like if you're trying to domesticate a dog from a wild wolf. If you have an aggressive pup in the litter, it keeps biting the hand that feeds it, you don't take it through to the next generation. You let it go and you keep the calm pups that are actually going to serve you well. The same thing happened with Aspergillus oryzae. Harmful bacteria that contained mycotoxins, toxins produced by fungi, that would make people sick, were left out of the equation. And they found interesting ways by adjusting pH, even though no one understood what the power of hydrogen was, or what these molecules were, or what this fuzzy thing was. The name for koji comes from the Chinese characters for chrysanthemum flower. People thought it was just a small flower. It was like, what is this thing? You use analogies to kind of make sense of it, but they understood what it was doing, and they understood that it was useful, so they kept it around, and then slowly bred those lineages into the kojis that we have today. So, koji, when it comes down to it, a spore of koji, and that's how fungi propagate. So, a spore of koji floats along, lands on the grain, starts spreading its web. Sorry, I'm just going to draw this a little larger here. And starts growing cells that are called hyphae. And hyphae are the wispy white roots that you see in like cross sections of the earth in the forest that form the mycelial network that mushrooms use to kind of make their way in the ground. Fungi and mushrooms, very closely related animals, they produce the same thing, just on a very smaller scale. Those hyphae spread into the grain starch, then release the same enzymes, the same beta amylase that plant produces, but then harvest all the sugars for itself. And then by osmosis, it takes up all these newly formed nutrients to fuel its own cellular reproduction, to then multiply and thrive. And if you have a lot of grains inoculated with koji spores, eventually that koji will grow over all those grains, and those roots will form an interlocking network, a web, if you will, that basically keeps a lot of like single grains whole and intact. And then you make a cake, a koji cake. This also happens in tempeh in a very similar process. The koji then, what's called, saccharifies all that starch, and it makes all these grains extremely sweet. But again, cooking is timing, and just like malting, you have to stop the process before all of those sugars are used up. So after about 36 or 48 hours of growing koji spores on cooked grains, you end up with this very sweet grain that's in the form of a cake that you can then use for other things. You can put it in the fridge, you can roast it, that'll kill the fungus, you can freeze it, that'll stop the fungus in its tracks. But if you let this go too long, the fungus will enter its reproductive stage in its life cycle, start producing its spores, and actually use up. Don't forget, like, it's going through all this work, it's producing all these enzymes to break down starch into sugar to do something. And it'll start to produce spores, and all that energy will get used up, and the koji will no longer be sweet. So you have to stop it before it has the chance to use up all that sugar, and you do that at the 36 to 48 hour mark. If you leave koji for 72 hours, all the sugar will be gone and it actually tastes a little bit bitter and kind of still. It'll taste like, it kind of tastes like a mushroom brick, if you will. And it won't be sweet. It'll kind of be mushroomy and a bit bland and a bit bitter. So you never want that to happen if you're actually cooking with koji to use it. You want to stop it in its tracks. From there, you've made koji. It's amazing to use on its own. René's been getting more and more into it the longer I work in the lab, to the point where we make, ice cream sandwiches with koji as a wrapper. We barbecue it. On the barbecue, we make really dense cakes that you can then use almost like a nigiri. That's on the menu right now, served with sea urchin. So it is something that you can eat as a base product. But I talk about it in the book in such a way because there are classes of ingredients that are just ingredients. Lettuce is just an ingredient. You grow it, you can cook with it, you can eat it. But lettuce is not good at doing anything other than being an ingredient. Eggs are good at doing things other than being an ingredient. You can use them as an ingredient. You can fry an omelet and have your breakfast. You can also use them as a tool. You can whip egg whites, pour it into a consommé, into a cloudy stock, and clarify your consommé. You don't need to use the eggs afterwards. They might impart some of their flavor into your stock. But you've used an ingredient as a tool. Koji is the exact same. You can use it for what it is, and you can also use it for what it does. So those enzymes that koji produces don't just get to sit there and do nothing after this. They're in there, they've been produced, they're sitting in this sweet grain, and now you can take that koji and add it to other products and have those enzymes run through a second life. And that's a distinction that we make called primary and secondary fermentation processes. A lot of times you'll think about fermentation as like a living organism actively doing a thing, and the act of that organism living its life, dividing, multiplying is the act of fermentation. In a lot of cases it is. Everything we've seen up until now is a primary fermentation process. You're growing the lactic bacteria. In that process, they're producing the lactic acid, and that is the process of fermentation. This is a primary fermentation process. You're growing the koji, is transforming the grain, but the grain is now a fermented product that you can then use to do completely other things in which no active living cycles are going on. If you take soybeans and mix it with koji and put it in a container and leave it alone, you will get miso. And that's because the koji, all those enzymes that first worked on breaking down the starch, can then be reused and act on starches in other products. So if you have starches in beans or in legumes, split peas, fava beans, soybeans, those enzymes will get a second life and start breaking down all the starches in those second products and producing what? Again, more sugar. But like I said, no organism works in this kind of black and white landscape. And koji is very good at producing a whole bunch of other enzymes that can also be used for other processes. So in this germ, what else is there? There's a lot of protein as well. Grains are extremely high in protein. They're the ones that humans have domesticated over the years. Koji also has a chemical toolkit, an enzymatic toolkit for breaking apart chains of amino acids or proteins. So just like we drew that chain link of polysaccharide, you can also draw a chain link of amino acids, the basic building blocks of life, the stuff that DNA codes to put together in a ribosome, and end up making, this is an artist's impersonation of protein, but that's kind of what they look like. These complex folded molecules of these linked amino acids. Again, lots of living organisms can produce enzymes that can then snip these proteins and allow them to float free, no longer linked together. They can kind of wander off into the distance, and these are free-floating amino acids. Koji does this extremely well. It produces whole flights of proteolytic enzymes, as they're called, proteases, that can snip apart proteins into their constituent amino acids. Now, why is this important? Why is turning proteins into amino acids an interesting thing?
Umami.
Umami. Exactly. All life is made from other forms of life. The living earth is just this constant recycling organism that takes life, breaks it down, builds it back up. And a lot of these molecules get recycled hundreds of thousands of times. The amino acids, they can be produced from base chemical molecules, but a lot of times they're just broken down from the living organism and then built back up in some other way in another organism. That's what metabolisms and feeding and growing your body actually is. And if you think about it that way, amino acids are extremely valuable to living organisms. And if something is valuable to you, you want to have a way of detecting it. Just because you say there's gold in them Dar Hills, you actually have to find a way to actually look for it. And you can't just take a plot of land and pay $10 million for it and say, I'm rich. You actually have to find a way of getting it out. And if you have a very good way of finding gold, let's say a metal detector, then all of a sudden, you're actually quite rich. The same way it works in gold hills, it works in animal bodies, especially mammalian bodies. And mammalian bodies are extremely fine-tuned for being able to detect free-floating amino acids, and one in particular that kind of stands as a marker for all the rest. But odds are, if you're eating something with this one particular free-floating amino acid, and it sets off a chemical sensor in your tongue that sends a message to your brain saying, eat more of this, there's the good stuff that I like, that I need to build my body with, you find that thing delicious. And this is where taste becomes a really philosophical thing, but it's best exemplified in koji and the process of umami, but taste is Darwinian. Taste is an evolved trait that is your body's way of sensing the world around it. The better you are at tasting the things that your body needs to grow, the more fit you and your offspring will be. If you have a gene that's really good at detecting glutamate, glutamic acid, and you then have a preference for tasting things with high amounts of these amino acids, you're eating a more nutritious diet. So, all of a sudden, a chemical pathway that happens on your tongue from an organism that's able to break apart proteins, outsource the work of digestion for you, then becomes a very sought-after thing, and people develop a taste that's reinforced for all their kids that also like the taste of this flavor through the generations, and human beings develop umami as a sense, and something we enjoy quite a lot. So that's kind of the cool thing about it. You can ask Gabriella Morini about bitterness and how that's the opposite end of the spectrum, but that's the idea there. So when you taste free-floating glutamate, it's normally often attached to sodium chloride ion to form monosodium glutamate, excuse me. You're realizing that the thing that you're eating isn't just delicious because it contains protein, but because a lot of the hard labor that your body would have to spend to break these proteins down into amino acids has been already done for you. If you can save your body the energy of doing something, you're saving calories, and a calorie saved is a calorie earned. In a very harsh environment where you have to forage for food to stay alive, if your body didn't have to go through some chemical process to break down food and digest food, it was then more nutritious for you. And this is why we have these compounded incentives for tasting and enjoying umami. When koji's enzymes come into contact with protein-rich legumes, like soybeans, like fava beans, like peas, it makes a lot of umami, and that's why these fermented products are so delicious to us. Because we can clearly tell that this work has been outsourced, things are broken down, ready to be built into the things that we need to survive, and we love them for this reason. And that's why we've kept koji around for thousands of years, because it's very good at doing this. Koji creates umami. There are a lot of other processes in nature that also create umami by breaking apart proteins into the constituent amino acids, but this is one that's really cool and interesting because it's not just relegated to the ingredient itself. You could make umami by making fish sauce, but you're rotting that fish. Here, we have something, like I said, akin to egg white, something that is its own thing, but you can add to other things to coax umami out of all those other things. And so half of this book is kind of uses koji in this way to make other things have different or interesting or umami-rich flavors just by using koji as a tool. It's an amazing ingredient in its own right. You can cook with it, you can fry it, you can find all sorts of clever ways to turn it into flour, stew it into stocks, barbecue it, grill it, roll it into pâtés, whatever you want, put it into sausages. But at the same time, you can also make a whole flight of other secondary fermented products like misos, like garums, like soy sauces that utilize koji for its enzymatic powerhouse. Cool. We're good there? Questions? Yes, sir.
Where would you be able to get the koji for?
From someone who has them. So this is a super important thing that you really have to hit home to maybe amateur fermenters. But that's the question I often hear. It's like, oh, if I don't have a kombucha SCOBY, how do I make kombucha? You get kombucha SCOBY. If you want a golden retriever from your mom for Christmas, you want a puppy, she has to go to a breeder and find a pregnant golden retriever. All life comes from life. All cells come from cells. This wasn't always known, and this is why I hate Aristotle for his theory of spontaneous generation. But all life is an unbroken chain of organisms breeding offspring that were genetically quite similar to their parents, going back 3.5 billion years to the life or to the dawn of our last universal common ancestor, somewhere in a hydrothermal vent in the Pacific Ocean. All life is that, and you cannot get any life to do anything for you unless you have a parent organism from which it came. Yes, there are organisms floating freely, but those organisms came from other organisms. Just because they're all around you doesn't mean that they just come for free. There are places on Earth where you won't find them, and you have to get them to make them do what you want. Koji is one of those things, and especially because koji is a domesticated organism who has relatives that are quite harmful for you. When you have black mold growing in your apartment, maybe some of the student dorms in Prague, actually like, oh no, I wish I didn't live here. That is actually a relative of Aspergillus oryzae named Aspergillus niger, and it will produce toxins that you will breathe in that will make you sick. Because it is an organism that's trying to fend off its territory and say, no, this is for me and me alone. I want to live here and nothing else gets to live here. I'm going to produce toxins that make a harmful environment for everybody else. By breeding out those by defanging Aspergillus oryzae, we've made it safe for us to consume, and that's an especially important reason why, when you are making koji, you want to actually get a species that has been verified, that's tested in a lab, that does not produce toxins. Because there is a chance to be mistaken there. So, that's that. Yes, sir?
I heard about meats inoculated with koji.
Mm-hmm.
It seems kind of dry-aged meat. Have
Yeah.
you tried it, or do you think something about it?
I'm not a fan of that. There are a lot of people that do it, and you see it all over Instagram.
Why you're not a fan?
Because I think it's kind of dumb. So, koji, while it does produce proteases, will not just grow on meat. If I get koji on my arm and go home, the next morning, I'm not being fermented. I'm not being covered in mold and being digested from the outside in. That's because koji cannot grow on flesh. It has been specialized. There are molds that do. It used to be a butcher. You could have a very moldy fridge. But the point is that koji specialized to work on the environment that is a grain. All organisms are kind of this mirror image of the environment that they live in. Just like a puddle of water, the water forms the exact opposite shape of the cavity it sits in. Organisms are the same thing for the environments that they live and thrive in. They actually have information about the world that they live in and make specialized chemicals and molecules to be able to interact with that world in very specific ways. And if you take a puddle, freeze it, and then try and put it inside a square container, you'll find it won't fit. And it's the same thing for living organisms. If you take koji and try and dust it on meat, it won't grow. It'll just get wet, it'll drown, nothing. You can keep your meat in an incubator for 3 days, it'll rot, your koji's not gonna grow. So when you see that on Instagram, here's what's happening. People are rolling meat in rice flour and then inoculating the rice flour with koji. So if you think about that, what's the koji actually working on? It's on the rice flour. So it's digesting the rice flour, and yes, there are enzymes that then seep into the meat just by being in contact with it. But you're also keeping meat at 30 degrees for 2 days, and I'm like, why? Like, I would never do that in any circumstance unless I'm making sour sausages. And there's safety controls to make sure sour sausages go right. But in this instance, there are no safety. So it freaks me out for a bunch of reasons. But then, like I talked about koji being a tool, if you just take finished koji, blend it with water, you make a paste that you can then rub on your meat, put in a vacuum bag, leave it in the fridge where it's safe, and the enzymatic breakdown of the meat from all the protease works better than if you grew the koji on rice flour on a piece of meat in a dehydrator. So when I see this technique, I'm like, sometimes people get carried away and get really enthusiastic, and I'm not saying the exploration isn't good, but that is something that we've tried, and we're like, this is categorically worse than doing this other thing that's more direct. But sometimes people like to hold up a moldy piece of meat and say, look at what I did, so whatever. Anyway, speaking of koji meat, we're going to talk about garums. I briefly touched on miso. Okay, we're going to talk about miso a little bit too. So, miso is far and away, this is my quick cake of koji. Miso is your koji cake, your soybeans, cooked of course, and salt. That's molten salt right there. That's what it looks like. These three ingredients make magic. That's what this is. This is piso from restaurant Noma. And I thought this batch was going to be smaller, so initially these were going to be tastes, but we don't have to go around. So you can just pass this around and give it a smell, but it is a fascinating smell. And this is yellow peas, which grow in Denmark. Because soybeans don't. Barley koji. Barley grows in Denmark, rice doesn't. So we've taken these processes from somewhere else, put them through the lens of where we said we were going to work, find ingredients that kind of hit the same notes, that act as very similar environments to where this organism originally came from, and then create something wholly new. And that's one of the coolest things about fermentation, is once you understand it, these aren't just recipes. You can treat them as recipes. And you can say, add A to B to C, and I'm going to get a souffle. You can say, add A to B to C, I'm going to get soy miso. You can also say, sub A for X, B for Y, C for Z, and you end up with something completely new. You take the process, analyze it for what it is, then put in different inputs, and you get a completely different output. And no matter where you are on Earth, I guarantee there is something that has not been fermented in whatever style. The world of fermentation is not a subset of the world of cuisine. It is equally large, if not infinitely larger than it. But you have to understand the processes and treat them like algorithms or tools to be able to access this whole other world of undiscovered flavor. But that's kind of the beauty of this book. Once you understand the processes, you're free to do whatever you want. It's not going to be traditional, but it is explorative, which is kind of the best part. You're going to have some failures. Some things won't work as well as others. Maybe koji doesn't like to grow on buckwheat for whatever reason, but it can grow on rye. No one in East Asia ever grew rye koji, because rye isn't endemic to East Asia, but it grows here in Europe, so you can do that. And now you see all the possibilities of taking different inputs, just in the way that we're talking about kombucha. Same thing applies for koji, same thing applies for misos. Different inputs will lead to completely different outputs, and you can find whole worlds of interesting new combinations because of it. When I was talking about miso being a secondary fermentation process, where even though the koji might be dead, or it might be dormant or whatever, being combined with a new fresh ingredient, you're getting those enzymes to get to work. Like I said, keep this in mind, sometimes I contradict myself, but it's fine. No process in fermentation or in the living world is completely black and white. And when you have a miso and you have these three ingredients going into a bucket, eventually, undoubtedly, you will also have yeast, you will also have acetic acid bacteria, you will also have lactic acid bacteria in there as well, eventually propagating. The less salt you add to your batch of miso, the more of these other fellows you see in there. Salt, again, a super critical control point for controlling how a miso ages and ferments. You try and keep things out and make it a safe environment for everything that needs to grow. Salt does have an effect on enzymes, but not so much so that it's going to stop the process and extract. And misos in Japan can be extremely salty, sometimes as much as 20% salt. Now, Noma is a very unsalty restaurant, René's palate, who likes to keep things clean and fresh. So a big challenge for us in the laboratory is finding a way to make misos as low salt as possible, as low in salt as possible, while still getting the ferment to work successfully and safely. So at 4% salt, we're keeping out malevolent bacteria, but also opening the floodgates to all of these other critters that we've seen before in the previous kind of lessons or bodies of fermentation. We allow it's get pretty easy for them to thrive in there. That's not necessarily a bad thing, because if all of these, if yeast and acetic acid bacteria and lactic acid bacteria all produce interesting and flavorful ferments on their own, when you add them to a feud and let them propagate in a vat of miso, you're going to make for a very interesting and complex miso. So that's something to keep in mind. The more salt you add to a ferment, the more straight and narrow it is. You're getting enzymes to do their thing, you're going to produce umami, but it's going to be whoosh, blinders on. A very one-note ferment. That's not necessarily a bad thing. It'll last for a long time, you can age it for a long time, and you'll get other flavors because of that. But the lower the salt content, the more other microbial activity will start to take place. And all these guys will have something to say. The lactic acid will make it taste sour in one way, the acetic acid in another. They'll hit different parts of your tongue. The yeast will start producing esters that make it fruity or floral, and you'll get notes that approximate apricots or nuts or things like that. In the same way that wine can taste of a million different things because of the yeast, because of the grapes, because of the combination of all of these aromatic compounds, the same thing happens in a miso, the more activity you have. So the less salt content, the more complex your miso. The higher the salt content, the more straight and narrow. Now you can make up for that. You can make up for straight and narrow miso being interesting by letting it age for a very long time. The longer a miso ages, the more Maillard reactions get to take place, and the more caramelized notes or interesting notes you'll have because of that set of chemical reactions, not necessarily biological ones. Something to keep in mind. Okay, speeding through. If we move on from miso and go into the world of garum, we're looking at kind of a system. So instead of soybeans, we're going to add meat. And it can be fish. So, koji, fish, protein, and salt can produce a garum. Garums, though, traditionally, in ancient Africa, which is where they come from, were normally produced just with fish and salt. But an important part of this process is that fish and salt can also have the capacity to take those long proteins and chop them up into amino acids if you use a certain part of the fish. And what part is that? The guts. What do fish do when they eat another smaller fish? They digest it. And how do they do that? With enzymes. So a fish, in and of itself, any large animal, actually contains the enzymes needed to break down that animal itself. Now you guys aren't all digesting yourselves here, turning into vats of fermented juice on the floor right now, because all of your digestive enzymes are closely moderated, kept in homeostasis by a living organism that closely monitors where these enzymes are going and what they're being used for. They're kept in sacs, they're kept in your intestine, they don't leak out. But if you just throw a fish in a blender, all of a sudden they do. And if digestive enzymes come into contact with parts of the fish that would normally be kept separate, i.e. the muscle tissue, it'll start to digest itself. Anyone know what this process is called? Say what? Yeah, but you said it wrong. Autolysis. Yes. And the verb is to autolyze. So yes, autolysis is effectively, from Latin, self-digestion. That's what that means. So, to autolyze fish into garum, all you need to do is add salt, and salt is only there to keep out bad microbes. Now, protein is one of the most sought-after, digestible things, free-for-alls in the natural world. A rotting carcass on the side of the road is fair game for anything to come into contact with it. Everything likes to grow in rotting meat. So you need to add a lot of salt if you're making garum that's just fish, its guts, and salt. Normally into the neighborhood of like maximum saturation of salt in a liquid, which is sitting at around 23 or 24% before it can no longer dissolve and be a suspension. It just sits as crystals in the bottom of a liquid. But garums are normally made with salt concentrations that high. If you're to make a garum just by leaving fish and salt rotting at room temperature for a year, You would need the salt to be that high, but I've gone down as low as around 18%. I would never go lower than that. Because if there's one thing in this book that's going to go off if you add too little salt and actually make you very, very, very sick, it's going to be a garum. Because meat will allow all sorts of harmful things to grow in it if it gets the chance. Enough salt though, and you're safe. Now people often think that fish sauce is stinky. And it is, because it produces a lot of different volatile aromas that you would associate with being quite smelly. But at the same time, it's not smelly in the way that rotten fish is smelly. It's pungent. It's strong. These are strong aromas, but it's not stinky. And if you get a garum made with extremely fresh fish, it will be pungent at the end, but it will also still taste like extremely fresh fish. This is a very important thing to remember when you're fermenting. Your fermented products, even though they take months to produce, just sitting in a corner or rotting away somewhere, are only as good as the ingredients that go into them. The fresher your products are when you ferment them, or when you start fermenting them, the better your ferment will be at the end. You can't just let something rot for 2 weeks, then say, oh, I'm going to turn this into something and save it, and expect a good ferment at the end. No, you've started with bad first primary ingredients. You're going to get a bad finished product. So that's always something to keep in mind. And even though a garum might be made of rotten fish, if that fish is fresh, your garum will actually taste good at the end, even though it's still strong tasting. The strong tastiness, the pungency of that garum doesn't come from, like I said, rotting fish flesh or the smell of bacteria eating fish organisms or breaking down fish fat. It comes from those digestive juices. Just like eating offal of any animal is actually like quite an experience, so too is eating the offal of fish, even in the form of a stewed fish garum. So at Noma, if we want fish to be, or a fish garum, or any garum for that matter, to be extremely clean in flavor, we leave all of the heavy notes of fermented guts out of the equation and sub in koji, which is good to eat on its own. It has a delicious flavor, it's sweet, it's floral. That's the other thing about koji. It has a flavor in and of itself. The actual fungus has a taste, and it's really fruity, and it's really amazing. And that's a really cool feature about it. So you add a bonus of all this delicious flavor, all the enzymes that you would normally harvest from the fish. You leave out the guts, say, I'm not going to use that, just use the flesh, add your salt, again, at a high salt concentration, let's say 18%, let it rot. Some microbes can survive it. Salt content's that high, and in 6, 8, 12 months' time, you get an amazing concentrated liquid. You can strain off the solids. Some of you might know this as colatura di alici. Some of you might know it as squid gram fish sauce. Some of you might know it as ancient Roman garum, but it makes cooking that much better and easier. Just a splash of it fills whatever you're cooking, your stir fry, your stew, your pasta bolognese, with all this umami that makes you want to eat more. It triggers this underlying fluttering sensation that what you are eating is inherently delicious for all the evolutionary reasons we talked about 10 minutes ago. Super cool process. In this book, we also sometimes ferment our garums in the heat. And this is an instance where you see me checking up on something in the lab. But some of these garums are fermented at 60 degrees Celsius to accelerate Maillard reactions on purpose. And that actually doubles up on a safety parameter, which is heat. Like I said, if you have microbes at 60 degrees, they're going to die. They're not going to produce any harmful toxins that'll kill you. So you use heat as an additional safety parameter, compounding it with the salt, and then you can actually lower the salt content. So you can make a less salty garum by adding heat. You get a different flavor than if you just left it at room temperature to kind of fester and do its thing. But at the same time, you just end up with a different product. So that's always something to think about, is that heat can be used as much as a safety parameter as an anaerobic environment, a lack of oxygen, or salt, or pH. So there's a lot of tools at your disposal. And once, like, the more you ferment, the more you understand fermentation, the more you can understand that you can mix and match things and get different results because of all these parameters. That it really is like playing at a giant control panel where food goes in one side, microbes come in another, and you get a finished product. And switching those knobs will yield different results. Yes?
Obviously I didn't get something right. You said using the koji on meat is a dumb thing. What makes it less dumb using it on fish? Is it just that you use different parameters?
You're just looking for a different result.
Okay. Okay.
I think the thing with growing koji on meat is like, oh, I have this super tender, umami-rich steak, and then you cook it as a steak and eat it as a steak. And you can do that in a much more safe and controlled way by just blending koji and marinating your steak in koji, in blended koji, because all the enzymes are there and grown, right? That to me is a smarter way of going about getting one result than another. In this instance, you're making a completely different product. And again, you're not growing the koji on the fish or on the meat you're looking to ferment. You're combining them and letting the koji's enzymes work on those proteins to make a liquid that you can then use as a seasoning. So what you're looking to do, the intent, the thing you're looking to create is very important to how you consider going about a process. If you want a finished steak that has some aspect of fermentation in it, and you're trying to make it more delicious or heighten it in some way, and you're not just fermenting for the sake of fermenting, but you're trying to accomplish something, then you have to think about what steps it takes to get to that point and how that point's going to be at its best. And for me, when it comes to the conversation about growing koji on meat, marinating koji in meat, that's a better process. When it comes to making a garum, if you don't want it to be pungent, use koji blended together, you'll get a finished liquid that is delicious and roasted and tasty, but you haven't used it in a way that doesn't make sense. If you try to grow koji on meat and then blend it into water and salt and then be like, oh, I'm making a garum that way, that's a dumb way to make a garum with meat and koji. You see what I mean? Because you're just opening yourself up to more avenues for danger or things going wrong or a lack of control, basically. And control is very important in fermentation. Okay, that's garum. Next up, soy sauce, or shoyu. Shoyu is a fun one because I guess technically you could make it by taking finished koji and taking soybeans and then combining those two things in a salty brine. Basically, it's almost exactly like making garum, kind of halfway between making a miso, but you add soybeans, and then this salt is in the form of a brine. So it's a liquid, it's basically like liquid miso. That's actually how it came about. Misos came before, they preceded soy sauces. And if a miso is wet enough, eventually, and you should keep a miso underweight for all the same reasons you would keep a lacto-ferment underweight, eventually a bit of liquid will form at the top and create this kind of like airlock or a seal. Anyone know what that liquid's called? Tamari, exactly. So the tamari that would form on top of misos as they fermented in a vat was such a tasty kind of byproduct, people were completely enamored with it in Japan, in China, and it became an industry unto itself. And tamari, the characters for it translated from ancient Chinese characters, literally means, or it means like paste liquid or paste oil. Oil is what they would use, or what they would call like any viscous liquid. So it means like paste liquid. Eventually, but you have to make a lot of miso to get a little bit of tamari. So it wasn't this completely sensible process just to make one thing to get a byproduct of another. So they adapted the recipe to make soy sauce its own thing that hit all the same notes as tamari does. And to do that, they grow koji cakes of your soybeans with wheat to kind of soak up. You have to cook the soybeans because the mold is going to have no chance of growing on it if it's just a hard, uncooked bean. So you have to boil your soybeans. You mediate the moisture content because you don't want to drown your spores by adding cracked wheat, and then you let the koji grow on the beans and the wheat. All of that goes together in a brine, and then your soy sauce ferments, or the secondary process of all these enzymes swimming around in the salty liquid takes place over the course of months or years. And Maillard reactions come into play as well. It ages, gets more complex. Very salt-tolerant yeasts get to propagate in there and add their flight of volatile aromas into the mix as well, and you get a really complex and delicious thing. There's ways that chemists have devised to cheat this whole process, using hydrochloric acid to make what's called chemical soy sauce. The stuff that you get from like a Kikkoman tin can that tastes really flat. It's like, oh, this is soy sauce, it's not interesting. That's often made in very strict kind of factory conditions, sometimes using hydrochloric acid to break down protein chains into glutamate. The natural process is far superior. And again, it's superior because you get all of these other microbes coming into play, adding their voices to the fume, making your finished product artisanal, interesting, layered, and complex. And that's a really important distinction to make when it comes to fermentation in that regard. Again, you can ferment a whole other world of legumes and grains into soy sauce. We've made soy sauce from split peas, we've made soy sauce from lentils, we've made soy sauce from black beans and cranberry beans, and they all do taste fairly different. The longer you let them go, the more they'll converge on just a dark Maillard reaction flavor, but when they're young, you'll notice that they are quite nuanced and different from whatever those initial products were. So again, soy sauce in East Asia is made from soy, and that's how it's done. But once you understand that process and open it up to whatever you have in your region, you can create whole new flights of flavor that have existed nowhere else on earth just because of where you are in your own terroir. Taking ideas from somewhere else and applying it to your region. Super cool. So that's soy sauce. Everyone knows how to cook with it and use it. It's delicious. A little splash goes a long way for the same reason that a garum is really delicious as well. This is a beef garum up here. Can we pass this around and not spill it? You can smell it. It smells like roasted meat. Okay, we'll do that. I don't think people are going to smell it. And then this next one is a shoyu that we steep with seaweed. So you can listen. And these are very salty, but you can smell that like the beef garum really does smell like roasted meat. It has this strong, but you can imagine adding that to a bolognese and like really upping the beef flavor. And then this seaweed shoyu, where we add seaweed to the final steeping when it's actually fermented. Tastes like, it smells almost like a fruit juice, but it also has that flavor of soy sauce.
Which seaweed do you like?
We use kombu that we get from Japan. We went to Japan and fell in love with the kombu maker there, so we use Japanese kombu. All right, so that's the world of koji, by and large. The only thing left to talk about is something that isn't actually technically fermentation, but black fruits and vegetables. And to do that, we will, yes sir?
You just said you have the kombu or the seaweed at the end. How does it work?
It just, so you have your, so let's say that this is peas and wheat, and I made a koji cake from it. And the koji grew all over those peas and wheat. And then I put that into a jar with salt water. So there's my brine, and then whoop, that goes in, and it just sits there, and then like, it's safe, it's salty enough. The enzymes are doing their thing on all the residual untouched starches in there, and it gets to age and get caramelized. You can throw in other products at that stage and have those products age and add their flavor to what you're doing. And so for this, we add seaweed at that stage, and it gets carried through, and you get this kind of oceanic flavor. It releases all of its umami, because seaweed's super high in glutamate itself, and you get a really complex. Again, it's cooking. There's no hard and fast rules. You can do things that aren't normal and get results. You can make a celery vinegar and then steep it with fresh parsley at the end for like a day and have this like tincture. You can do anything you want. It's cooking. You can make recipes as complex or as simple as you choose to. If you understand the points where flavor extraction is going to make a lot of sense and work well. Cool? Yes?
So for this, the koji of the cake, does it need to be submerged in the brine somehow?
It needs to be covered with salt water. So that's the environment. Just like making brined pickles, you need your cucumbers to sit under the same thing with this. Because otherwise it's not going to stew and break down. Yeah, it's very important. Okay, black. We're just going to talk about black garlic. Anyone know how this is made? No?
Very slow Maillard.
Yes. Yes. Yes, it is. So, heat is a fascinating thing. And when we're talking about storing garums in the heat, letting them caramelize slowly, we're talking about very slow Maillard reactions. Can anyone here explain the Maillard reaction? I know you guys know this one. Come on. You said ovalize, you know it.
The reaction between proteins and sugar?
Yes, exactly. So reducing sugars, you don't have to get into the chemistry in it or what the electrons are doing, but when reducing sugars come into contact with proteins, you can get a whole flight of aromatic compounds, browning compounds as they're called, that add color and flavor and that characteristic Moorishness, that like seared steak flavor. All those flavors come from the breakdowns of proteins and sugars, normally being smacked together at high heat. Normally heats in excess of 170 degrees Celsius, am I wrong? Anyway, that's normally the required temperature to force Maillard reactions to happen. Reactions either take energy to undergo transformations or release energy to undergo transformation. When you break apart glucose, you get energy. A little spark goes off. That's something that you can use. If you're trying to break apart molecules that normally are very stable and don't want to be broken apart, you need a lot of energy to force it to react by smacking two things together and then getting different products out of it. And that normally doesn't happen in baking bread or searing meat in a pan until you hit 170 degrees Celsius. Now, an important thing to note about 170 degrees Celsius is that it is fully 7 degrees above the boiling point of water. So normally, if you have water in whatever it is you're trying to caramelize or let undergo a Maillard reaction, nothing's going to take place. Why? Because the water is acting as a thermal sink that is not allowing any of those reactions to get energetic enough to undergo a Maillard reaction. To take a reducing sugar, to take a protein, smack them together, away you go. That's why you get Maillard reactions where? In a steak? In the pan, where it's being seared against that hot metal surface. The water is being flash evaporated, and you get that crust. Where? In an oven? On the crust of bread, where that hot air is in contact with the flour, with the proteins in the crust. That's where you get a Maillard reaction, not in the center of the dough. Maillard reactions don't take place all through a product at the same time. They take place in the contact where water can evaporate and then allow the temperature to rise enough to force an energetic reaction that breaks apart a protein with a reducing sugar. Ta-da! That's that. So, if black garlic is transformed, I'm not going to say fermented because it's not fermented, at 60 degrees, how are we getting Maillard reactions? Garlic's wet. It contains a lot of water. Everyone knows that. So how are we getting Maillard reactions? No. I mean, but no. Who said? Huh?
Oxidation.
Also no. No? Temperature. Yeah, temperature. You're right. And we touched on this when we were talking about temperature before. But temperature is the kinetic energy of molecules in motion. The greater the kinetic energy, the higher the temperature. The important thing to note is that in even this paper cup, there are trillions and trillions of atoms. Whoops. Not all of those atoms are moving at the same speed. But I can look at this cup and say that it has a temperature of 22 degrees Celsius because I am taking an average. That average looks like this. That is the thermal curve of any black body emitting thermal radiation. Let's say that I'm holding a clove of garlic at 60 degrees Celsius. This is what 60 degrees Celsius looks like, so that's what we can, it's like, okay, yeah, most of the molecules in here are moving at a kinetic energy at a level that approximates 60 degrees on the whole. Some of them have just bounced around a couple molecules in a back and forth motion and are now actually moving much slower. And maybe they're moving at the equivalent immediate energy level of, let's say, 30 degrees Celsius. But, by that same token, sometimes molecules will ricochet at such a speed that they end up getting knocked around really, really quickly, and any individual molecule might actually be moving at the equivalent energy level of 170 degrees Celsius. Now, the thing about this bell curve is that the higher you move it along a range of temperature, the more likely you are to actually have a molecule initiate a Maillard reaction. So a product held at 30 degrees actually has a much lower probability of eliciting a molecule moving fast enough to elicit or to start a Maillard reaction. But something held at 60 degrees, if left for long enough, will produce enough of those energetic molecules to break apart or smack together, reducing sugar and a protein to start a Maillard reaction, even in the presence of water. And eventually, if you leave something for long enough, it will blacken. And that's how blackening fruits and vegetables work. You're waiting for those rare instances over a long enough time in a region of temperature, of average temperature, that you're going to push something, if given enough time, into being a fully blackened state. And that's why black garlic blackens from the inside out in a way that bread or a steak does not. That's basically what it is. And so to correct myself here a little bit, yes, there is also oxidation. Yes, there are also browning enzymes that also take place and add to the complexity of black garlic. But for the most part, that slow Maillard reaction is just a probability curve in temperature. Leave something for long enough, black garlic will eventually taste burnt as if you burnt garlic in a pan in high heat. So think about blackening as the area under a curve. If you leave something at a low temperature for long enough, the area under this curve, let's say temperature and let's say time, the area under this curve at a very low temperature, 25 degrees, will eventually lead to something blackening because of this reason. If you put something in a pan and have a really high temperature for a short amount of time, again, you've now inverted the curve, but you still have enough area under that curve to force enough of these Maillard reactions that you're going to taste carbonization or burnt flavors. So you're just shifting the scales of time and temperature. You can burn something in a pan, you can burn something by leaving it at 60 degrees for 3 months. But like I said, fermentation, all of these slow cooking techniques are still cooking, and timing matters. As much as you don't want to overcook your medium rare steak for your guest, you don't want to overcook your black garlic. So at that time period, in between, let's say 6 to 8 weeks, your garlic will reach that sweet spot where enough of those Maillard reactions have happened that it has this amazing flavor, this amazing aroma, where it's blackened. It tastes caramelized, it tastes deep and rich. And other things have been broken down to produce all sorts of volatile aromas. And you catch it at that moment, even though it's a day and not an instant, and you say, it's ready today. And then you pull it off, you keep it in the fridge, and you use it for whatever you want to use. Moisture content is also super important. So these molecules actually have to move around, and actually swim through water to hit each other. If your garlic dries out, that'll stop happening. You'll just have dry, hot garlic, and actually these Maillard reactions won't take place. It'll be too hard for the molecules to actually jiggle and hit each other. So a little bit of moisture retention is also super important. The easiest way to make black garlic, just put it into a Tupperware. Honestly, something like this. Just put it into a container like this. You can wrap it in tin foil. I've seen that. I've seen people just put it into a rice cooker and then saran wrap the rice cooker so no moisture can escape. But it is important to keep some moisture in there and then let the thing ferment. Not ferment, but just age. So that's blackening. It doesn't just take garlic, but garlic works really well. Why? Because it's pungent. It's not going to lose its initial taste. And it also has a lot of sugar in it. A lot of sugars that are available for these Maillard reactions. So if you're ever thinking of exploring the world of blackening, just keep those two things in mind. It needs to be able to retain moisture. It needs to be able to hold its shape so it just doesn't turn into a puddle on the floor. And it needs enough sugar to be able to undergo a Maillard reaction, and also enough flavor to be able to be recognizable in the end. And that's how you do that. That is the entire contents of the book. How are we for time? Can I just rant, or can we take questions? Or cool. Just follow along. No, it's fine. I don't have anywhere to be. So this is a slideshow that I kind of show to some people sometimes. And I'll just kind of run you through what the lab looks like now, as I promised. But this is Noma. This is the lounge over here, entrance, the main dining room. And then this building extends off for 100 meters going down the road. And in there is where the lab, that's where actually the guts of Noma are. That's where the production kitchen is, where we have 25 interns prepping the cod bladder, or picking herbs, or making leaves perfect shapes. And also the lab is situated in there as well. Now, when we started working on it, this is what it looked like. It was just an empty room. I have the fortune of having a skylight, even though I'm at the back of the building, I got some natural light in there. And it really was just a blank box for me to start filling up as kind of my dream kitchen. So we have kind of a central workspace. We have a bench on this side that's very much a functional kitchen. That's where our oven sits. We're actually in a research contract with Rationale. And they've donated one of their top self-cooking centers for us to actually work with fermentation programs, and maybe one day they can actually program into a Rationale oven. So imagine that, you're cooking in a fancy restaurant 10 years from now. And then you're like, oh, Koji said it. And then boop, and then you have an instant incubator. And then along the back, we have our centrifuge, rotavat, and then some other tools over here. That's what it looks like today. So as you can see, everything I described. We have a rotavat for distillation. We also use ultrasonic homogenization, which is a really cool tool. Yes, we're a fermentation lab, but we're also just like the lab at Noma. So if something needs to be done, if something needs to be figured out, we have a lot of tools that just deal with the states of matter, deal with food processing, that can allow us to do really cool stuff. We also have a lab-grade centrifuge for spinning blood. It's kind of like the biggest they can get, and we can do 3 liters of liquid at a time in there. So again, sometimes we want to clarify a ferment, and we don't want to spend a lot of time letting something drain for a week to make sure it's completely dry. So we'll spin it in the centrifuge, and you get all your phases back. A solid portion, and then your super clear liquid when you spin 4,000 Gs. We have a mixer that we use to actually mix the batches of miso and grind our proteins or whatever for garums. And then this over here is a fun thing, but this is what's called a supercritical fluid extractor. And just a little aside, but again, the lab just deals with science at the restaurant. And I had the pleasure of going down to the south of France a while back and actually staging at perfumeries to understand how they extract flavor. And SFE, as it's called, is a really amazing, it's basically the most powerful form of flavor extraction known to man, where you take carbon dioxide, pressurize it to a point where it becomes what's called a supercritical fluid. Anyone know what that is? No? It's a fluid. Say what?
It's between two phases, right? Between fluid and gas? So, yeah.
It is a phase in and of itself that combines properties of both being a liquid and a gas. So liquids are cool as a state of matter because they're very hard to compress. You can compress water a little bit, but at some point the molecules will just butt up against each other and they're not going to go anywhere, and that's why pneumatics work. But a gas is amazing because it's also diffuse. If you open a balloon in a vacuumed room, all those molecules will spread out to fill the room equally. A supercritical fluid is as dense as a liquid while also being as diffuse as a gas, which kind of seems contradictory, but that's why it's super useful. So if you run a supercritical fluid through a cherry, it will enter the cherry at every pore possible without ever being able to expand. And so in doing so, it becomes an amazing solvent. So carbon dioxide above 35 degrees Celsius and above 74 bar of pressure becomes a supercritical fluid that can then strip organic molecules into its stream, just like ethanol can take paint off of or Sharpie off of a whiteboard, and then at some point you release the pressure and all of the dissolved solutes in that stream precipitate out, and it literally rains the one thing you want. Now that's cool in and of itself, but the cool thing about SFE is that by controlling temperature and pressure, you can categorize what size of molecule you want, or the polarity of the molecule. So you can take really specific things. And this is super cool with food because this was actually developed by the coffee industry as a way to make decaffeinated coffee beans. So they calibrated a recipe or a set of parameters in an SFE unit that would take just caffeine out of coffee beans and leave all the flavor molecules behind. So it's as good as extracting one specific thing as it is taking out one specific thing. Now, I don't think there's any other restaurant on earth with one of these machines inside their walls, but the possibilities for this technology and food are like crazy beyond. You can add solvents to the stream of CO2, have it pass through your main ingredient, and then leave it there. Your main ingredient can be a piece of fish. You can add, let's say, butter, an ethanol mixture, to your CO2 stream, inject a solid piece of fish with the flavor of butter, and then have sashimi that tastes like brown butter, if you wanted to, on the inside. So there's all, and you think you're like, oh no, this is spacey, but like this is like a whole realm of molecular gastronomy that like Ferran and Adrian never even touched. Mainly because like this machine is $100,000, but it's also like the probability space, the potential of this technology to become like a restaurant-changing, cuisine-changing thing, if the machines got simplified or cheapened, is quite beyond. You can do really cool stuff with it. So that's something I work on in my spare time. Sometimes we need to extract ethanol that we put into the stream out afterwards, so we get a very concentrated and pure extract, and that's what we're doing here with the rotovat. That's sauerkraut that we made for staff meal. Other molds that we use in the lab, this is Monascus purpurus, that we've never been able, this is my unicorn, I've never been able to catch it. I can grow it in a petri dish and I can't grow it on grains. It sucks. This is how the Chinese used to make char siu 500 years ago. I don't know how they did it, because I can't do it. You try. This is squirrel garum. That's what squirrels look like. Squirrel garum is absolutely delicious. You know what it tastes like? It tastes like the juice that you get in like a vacuum bag of like Iberico ham. Like if you just like lick the bag. It's really good. This is an extract of forest floor that we're using on the Game and Forest menu last fall, and that's something that we made in the SFE machine. We basically took like a square meter of the forest, we got our foragers to bring it back, desiccated it, ran it through the machine, and it was like being like lying down in a bed of moss on like a rainy autumn day. So that was super cool, and we would scent the first course with that as like an edible aroma. This is a meadowsweet extract, seaweed extracts, frozen with liquid nitrogen. This is a cloudberry extract, a super rare berry from the Nordics. Yeah, so fun stuff that doesn't deal with fermentation. We work with like emulsions and extraction with the ultrasonic homogenizer as well. Going back, the centrifuge is really useful for things that you would never even think possible, like lysing, let's say, parsley juice, and taking all the fats and chlorophylls. Yeah, plants have fat in them, and if you have a powerful enough centrifuge, you can make pastes that are completely fatty and waxy, that are hyper-concentrated versions of the flavor. You basically end up with like brown liquid at the end, and everything good about a plant gets compacted into like a 10-gram portion that will like knock your socks off. So we use that on the menu sometimes. And yeah, it's a fun place to work. So that's my lesson. I hope you learned.
Didactic way to transmit all what they do and they know, and so I think it's also a good example for us to make complex things easy to understand. So great job.
Thank you. Yeah. So questions doesn't even have to be like about something to clarify. If you just want to ask me something, feel free. Your hand was up first, yeah?
Yes, a question about the book, about the object.
Yeah.
When I saw it first in the library, I thought like, okay, big book equals heavy book. Mm-hmm. And I took it, and it's quite a light book for
it's
big.
Very light.
I think it is a light book for
yeah.
bigger.
You can thank our publisher for that, Leah.
What?
Our publisher?
No, I don't know.
No, it's made of a very special paper that comes from Japan called Inso Classic. If you're a stationery nerd. But it's 80-gram paper, and so for every square meter of this paper weighs 80 grams. Normal paper that you get in a textbook normally weighs 120 grams, so that's why it's a very light book. But it's really nice.
No, the first
Japanese do everything better.
The first thing that came to my mind, like a well-made like bread loaf.
Yeah.
Big one, but light.
Thank you.
I think what.
Yeah. It's a good object. Yeah. Yes, sir.
Like garlic and the process behind it. I've seen like other chefs, other places, they do something with a double boiler and called like pyrolyzing different kinds of vegetables. Is it the same thing?
Oh, like pyrolysis?
Yes.
Yeah, so pyrolysis.
You can get black celery or something like that.
Yeah, but then you're taking it even further. So if you pyrolysis is like the thermal breakdown of molecules, where you're just like, and it doesn't necessarily have to be a Maillard reaction. with sugars and proteins. If you just smack molecules, you're basically burning it. And it's a controlled slow burn. So you take this process a little bit further down the line, and you're not just dealing with minor reactions anymore, but you're dealing with like thermal carbonization. And you can get interesting flavors out of that too. And again, so normally you can pyrolyze something by like putting it into a furnace at 400 degrees, toast. Or you can stretch that out and kind of, again, catch it at a very particular point. But blackening and pyrolysis are closely related. Pyrolysis does actually take place in a piece of black garlic in small quantities along with those other processes I mentioned. Yes, sir?
It seems like you read a lot of non-fiction books and into this whole non-fiction world, but what's the most important non-fiction book that you've ever read or that's had a big impact on you and your cooking kind of worldview?
The Structure of Scientific Revolutions by Thomas Kuhn. It's a very important book. It talks about how science works. And if you understand how science works, you understand a lot. And it's not just like, oh, it's like a history of science. It's like a fundamental, it's the best short, and it was written like 70 years ago or something, like in 1930, I think. It talks about what science is like at a philosophical level and how you come to know anything at all. How paradigms are formed, what paradigms are. And if you understand that, you can understand how knowledge is created and can be broken down and can be rebuilt. And it is a very widely applicable set of tools to understand the world. It doesn't matter what field you're in. I wish everybody read this book.
Can you repeat the name again?
The Structure of Scientific Revolutions. That's up there. And another book on epistemology by the astrophysicist David Deutsch from, I think, Oxford, called Gateways to Infinity. 2 highly recommended books. Also Richard Dawkins' Selfish Gene, also very important. Even though it's like wrong, it's still very insightful. Is wrong today. Science evolves. It's fine. Doesn't mean it wasn't good works in the 70s. Yeah. Yes, Sean.
How do you see Noma being one of the leaders in the restaurant business? How do you see them needing to take more responsibility on how to teach consumers who don't go to fine dining, but also in the fine dining restaurant, how they can be more responsible as a culture?
Through education, through someone giving René a soapbox and letting him say what he wants in the world. MAD is effectively that. I think René understood that, I was talking with Professor Marini yesterday. It's like, yeah, chefs have an enormous amount of power and sway and influence in the world today. They're given more attention today than they ever have been. And like Spider-Man says, with great power comes great responsibility. So MAD, the creation of that NGO, and you see Massimo Bottura doing it with Repertorio and things like that, is like, yes, if someone gives you a mic, I think you owe it to your peers and your fellow human beings to use it to say useful and helpful and beneficial things. And yes, at the end of the day, Noma is by no means obliged to help the rest of the world. It's just a business. It's a restaurant that's just trying to feed people and make money so that everyone can go home with a paycheck. But I think it's to René's credit that he's always thought that there's like a moral servitude that needs to go a step further. So, more of that. Yeah, in the back.
I would like to know how did you get
Speak up.
I would like to know how did you get to Noma and your interest and
How I got to Noma. I got to Noma by writing them a really long letter, and everyone was like, David, you're coming on strong, like chill out. But my cover letter was like 3 pages long, and in it I was like, this is why you should hire me. It landed on the chef's desk, and I heard the story after like about a year of me being there. Like, yeah, I remember the day that came in. We thought you were fucking crazy, so we just had to get you in to see what you could do. And then if someone gives you a shot, don't blow it. So I did my best on my trial and tried to impress them. And I started at Noma as a line cook. I was chopping the beets and prepping the pumpkins and things like that, sinking every day, getting screamed at by everyone. And then about 6 or 8 months in, I got the offer to move into the lab as just a sous chef to Lars, if you will. And I jumped on the opportunity. I never saw that coming. I had no I'd not worked in there, but I think people understood that I could understand scientific concepts pretty well. And I just ran with it. And now I run it and got to design a new lab and have a whole team and got to write a book, so yeah.
But did you start reading the books before or after?
Which books?
The one that you suggest.
No, long before. I've just always loved science. I grew up reading Carl Sagan and stuff, and it's just, yeah. He's my home. Yes.
What are you curious about now? What's next? Like food-wise, do you have like a checklist? How does it work?
No, I don't have a checklist. This wasn't on my checklist, and then I checked it off anyway. What's next food-wise? I think restaurants in the next, there's been a lot of exploring. Like we've gone from restaurants existing in the high courts of kings to feeding the wealthy in France and England, to being democratized and becoming international and mixing cuisines, and to the point where we're at today, where people are getting back to nature and foraging and fermenting their own foods and stuff. So yeah, we're like completing cycles and completing the circle. But at the end of the day, restaurants have always been expensive, especially for food done at this level, which is I think what most people are talking about when they're talking about restaurants. And I don't think it's sustainable. Magnus Nielsen talks about this as well. He's like, the concept of a destination restaurant is inherently unsustainable. We're talking about reducing our carbon footprint and, tending for the earth. You can feed someone a bowl of grains and give them a meal, and this takes very little energy. Or you can have a staff of 100 people work to form a symphony that is the pinnacle of high art. One of those things is sustainable, the other one is not. So I think restaurants in the next 25 to 50 years are really going to have to come to terms with what it means to exist, what it means to feed people, where moral lines should be drawn, and how much energy you should invest. There's a lot of talented and genius people helming the best restaurants in the world. If you take those people and say, okay, now feed as many people as humanly possible and make it as good for those people as possible while minimizing environmental impact, I guarantee you all their smarts and all their knowledge of food could do that. So how do you bridge that gap? How do you change people's perceptions of value?
Just like you said, education. Just like
Yeah.
spread your word.
Exactly. So we'll see where that goes. Yes?
Do you think that in future restaurants and chefs will feel the necessity to have a fermentation lab as you guys do?
If they do, great. Fine. It's really fun to ferment your own food, and it's not that much work. Once you understand it, you're like, oh, I can do this myself. And Dave Chang has talked about this before, it's like, just because there's some restaurant somewhere in Nashville, Tennessee that has its own chickens in its backyard, doesn't mean every restaurant on earth needs to make its own eggs. No, there's farmers for that. There are also artisans where you can buy fermented products from. But if you have the resources, or if you want your restaurant to focus on that, and you see the benefits of doing it, you can ferment yourself and save money and do interesting and creative things. It is a creative avenue like anything else. Not every singer needs to have a studio in their basement. They can also go to a studio. It's the same thing for restaurants and fermentation labs. If you're ambitious enough and you want to get into that side of the world, go for it. Otherwise, I'm sure this book will spur companies, if it already hasn't, of people who are making interesting ferments, who are then selling it to restaurants in their local scene, in Portland or Toronto or wherever, here in Europe. So if even that happens and people start making novel ferments and small businesses because of that, then we've done our job. Cool. Yeah?
Hi. How do you go about testing a new recipe? Do you have a certain method to your madness or
Yeah, so that's difficult to explain. You have a hunch. You can imagine that something might work or might not, and you take an educated guess, and then you kind of jump off the deep end. But it takes a lot. We don't have, at the end of the day, we're still a team of 4 or 5 people. We don't have an unlimited amount of resources. We have to do a lot of stuff for the restaurant and produce for the restaurant as well. So you have to kind of hedge your bets a little bit and say, what's an experiment worthy of doing? And then once you commit to it, then you take a very empirical like documented and regimented and rich approach and say, okay, we're going to try this one test in 35 different variants with 5% increase in this component or that component, and then you plot the best one, like we're talking about with coffee kombucha. But it takes a certain amount of intuition, just like being a chef. Any creative process needs you to imagine a successful outcome before you ever step foot onto the battlefield. So you need to just, and that's where being a chef comes in handy. You actually need the experience to understand what's going to be a worthwhile endeavor to pursue. Then you go for it. I said something funny to Professor yesterday, but one of the best little quips in pursuing research is ready, fire, aim. So you have your idea in mind, you take a shot, and then you sort out the shrapnel and make sense of it afterwards. But you still have to know what you're shooting at in the first place. Cool. We're good.